Have you ever stopped to truly consider what shapes the reality we experience every single day? We see the sun rise, we feel gravity keeping us grounded, we watch stars twinkle in the night sky, but what if I told you that everything we perceive is just the surface layer of something infinitely more complex and mysterious? Behind the curtain of our observable universe operates an intricate web of forces and principles completely invisible to our senses, yet they govern every single moment of existence, from the smallest quantum particles to the largest galactic superclusters. These are the unseen cosmic forces that sculpt reality itself, and they've been quietly at work since the very beginning of time. Think about it. When you look up at the night sky, you're not just seeing points of light. You're witnessing the aftermath of cosmic events governed by laws we're only beginning to understand. Dark energy pushing galaxies apart, dark matter weaving invisible gravitational nets, quantum fluctuations sparking particles into existence out of pure nothingness. These forces don't just exist out there in space, they're here with us right now, influencing the atoms in your body, the thoughts in your mind, and the very passage of time. We live our lives unaware that we're swimming in an ocean of invisible influences, each more fascinating than the last. That's exactly what we're exploring today, a journey into the hidden architecture of the cosmos. We'll uncover 30 of these extraordinary forces, from the quantum realm where particles blink in and out of existence to the cosmic scale where dark energy stretches the fabric of spacetime itself. This isn't just about astronomy or physics, it's about understanding the very foundation of what makes reality real. So settle in and open your mind, because by the time we're done, you'll never look at the universe or your place within it the same way again. Our journey into the unseen begins not in the vastness of space, but in the seemingly empty void right in front of you. If you were to zoom in on what looks like nothing, the space between these words and your eyes, you wouldn't find a true emptiness. Instead, you'd discover a seething, chaotic, and breathtakingly active realm known as the quantum vacuum. This isn't just passive emptiness, it's the very opposite. At the smallest scales of reality, space itself is a turbulent ocean of energy. Particles and their antimatter twins, called virtual particles, are constantly sparking into existence out of pure nothingness. They borrow energy from the universe, exist for an unimaginably brief instant, and then annihilate each other, returning the energy back to the vacuum as quickly as they appeared. This endless cycle of creation and destruction is what physicists call quantum vacuum fluctuations. It means that so-called empty space is actually a vibrant foam of activity, often visualized as a bubbling cauldron of potential. This isn't just theoretical, we have experimental proof. One famous demonstration is the Casimir effect. If you take two uncharged, perfectly smooth metal plates and place them incredibly close together in a vacuum, they will be gently pulled toward each other. Why? Because the quantum foam outside the plates has more room for these virtual particles to fluctuate, creating a subtle pressure that pushes the plates together. The empty space itself is doing the pushing. The implications of this are staggering. This quantum jitter is fundamental to the stability of atoms themselves. The electrons orbiting an atom's nucleus are constantly interacting with this sea of virtual particles, which subtly alters their energy levels. This fluctuation is even thought to have played a critical role in the very beginning of everything. Most cosmologists believe that a random, powerful quantum fluctuation in the primordial vacuum is what sparked the Big Bang, igniting the expansion of our entire universe from a single, spontaneous event in the quantum foam. So the very nothingness that surrounds us is not empty at all. It is a creative, dynamic force buzzing with invisible energy that is the foundation for everything we see and are. But if the quantum vacuum is the unseen canvas of reality, then the next force is the mysterious brushstroke that's stretching that canvas on a truly cosmic scale. We now journey from the infinitesimal to the infinite, to a discovery so profound it completely upended our understanding of the universe's destiny. This is the force of dark energy expansion. For most of the 20th century, scientists were locked in a debate about the ultimate fate of everything. Would the gravitational pull of all the matter in the cosmos eventually halt its expansion, causing it to collapse back in a big crunch? Or would it simply keep expanding forever, slowly cooling into a dark, frozen eternity? The answer, when it came, was something nobody had predicted. In the late 1990s, two independent teams of astronomers were studying distant stellar explosions known as Type 1, a supernova. These events are what scientists call standard candles. Their incredible, consistent brightness allows us to measure vast cosmic distances with remarkable precision. By observing how much their light had redshifted or stretched, the teams could calculate not just how far away these supernovae were, but how fast the universe was expanding when their light was emitted billions of years ago. The expectation was that the expansion, set in motion by the Big Bang, would be gradually slowing down over time due to the relentless grip of gravity. What they found instead was absolutely staggering. The data revealed that the expansion of the universe isn't slowing down at all. It's speeding up. Galaxies are flying away from each other at an ever-increasing rate, as if some unknown, repulsive force is overpowering gravity itself. This mysterious culprit was dubbed dark energy, and it remains one of the greatest enigmas in all of physics. We cannot see it, we cannot detect it directly, but we can see its profound effect on the cosmos. Current measurements suggest dark energy makes up about 68% of the entire mass energy content of the universe. It is the dominant force shaping our cosmic fate. The leading theory suggests that dark energy is an intrinsic property of space itself, a constant energy density permeating the vacuum, causing spacetime to expand. The more space expands, the more of this energy exists, creating a runaway feedback loop that accelerates the expansion further. The implications for the ultimate fate of the cosmos are both awe-inspiring and humbling. If dark energy continues to dominate, the universe will experience what cosmologists call a heat death or big freeze. Billions of years from now, the acceleration will become so extreme that distant galaxies will be pushed beyond our cosmic horizon, their light never able to reach us again. The universe will become a vast, ever-cooling emptiness with isolated islands of galaxies forever alone in the dark. This isn't just a far-off prediction. It's a process that's happening right now, an invisible force acting on an unimaginable scale, dictating the destiny of every single galaxy, star, and planet in existence. While dark energy works to push the cosmos apart on the grandest scales, another invisible force is acting in direct opposition, pulling the universe together to form its most magnificent structures. This is the profound gravitational influence of dark matter. Imagine trying to build a cathedral without any scaffolding. The entire structure would collapse under its own weight before it could ever take shape. In a very real sense, dark matter is the invisible cosmic scaffolding that allowed the universe to build the galaxies we see today. For evidence, we need look no further than our own galactic neighborhood. In the 1930s, a brilliant Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a massive group of galaxies. By measuring how fast these galaxies were moving around the cluster's center, he could calculate how much mass, and therefore how much gravity, was needed to keep them all bound together. The numbers he got were staggering. The visible mass of all the stars and gas in those galaxies was nowhere near enough to provide the necessary gravitational glue. Zwicky concluded there must be some unseen, dunkel materie, or dark matter, providing the extra mass. For decades, his idea was largely dismissed, but in the 1970s, astronomer Vera Rubin provided irrefutable proof. She meticulously measured the rotation speeds of stars within spiral galaxies. According to the laws of gravity, stars on the outer edges of a galaxy, far from the central mass of stars, should orbit much more slowly, just as Pluto, far from the Sun, moves much slower than Earth. But that's not what she found. Stars at the edge of a galaxy orbit just as fast as those near the center. The only explanation is that each galaxy is embedded within a gigantic, massive halo of something invisible, a halo whose gravity is pulling on those outer stars, speeding them up. That something is dark matter. We can also see this invisible matter through its incredible ability to warp the fabric of spacetime itself, an effect called gravitational lensing. According to Einstein's theory of general relativity, a massive object will bend the path of light traveling past it. A huge cluster of galaxies laden with dark matter acts like a giant cosmic magnifying glass. It distorts and bends the light from even more distant galaxies behind it, stretching their images into dramatic arcs and rings. By meticulously mapping these distortions, astronomers can create a detailed picture of where the mass, and therefore the dark matter, in the cluster is actually located. The resulting maps are breathtaking. They show vast, intricate webs of dark matter stretching across the cosmos, with galaxies and clusters merely forming at the densest intersections, like glitter sprinkled onto sticky threads of invisible spider silk. This dark matter web is the true backbone of the universe. In the early cosmos after the Big Bang, the slight clumps of normal matter were too diffuse and were constantly being blown apart by the pressure of radiation. Dark matter, being unaffected by light or radiation, was able to clump together first under its own gravity. It formed gravitational wells deep enough to then pull in the normal gas, providing the seeds for the first galaxies and stars to form. Without dark matter's gravitational pull, the universe would be a vastly different and much emptier place. We would not be here to ponder it. It is the unseen architect, the silent constructor whose invisible hands sculpted the cosmic structures we call home, all while remaining forever hidden from our view. Yet while dark matter provides the invisible gravitational architecture for the cosmos, another phenomenon challenges the very foundation of how we perceive reality, operating on a scale so small it defies all conventional logic. This brings us to one of the most baffling and spooky forces in all of physics, quantum entanglement. Imagine two particles, perhaps a pair of electrons or photons, born from the same event. According to the rules of the quantum world, these particles can become intimately linked, their properties fused together in a single, shared quantum state. This connection is so profound that if you were to separate them, sending one to the far side of the laboratory, or even to the other side of the galaxy, they would remain inextricably bound. Measure a property of one particle, like its spin or polarization, and its distant twin instantly assumes a correlated state, as if the two are communicating faster than the speed of light. This idea was so unsettling to the scientific establishment that Albert Einstein himself famously rejected it, deriding it as spooky action at a distance. Along with his colleagues Boris Podolsky and Nathan Rosen, he formulated the EPR paradox in 1935 as a thought experiment intended to show that quantum mechanics must be an incomplete theory. Their argument was based on a principle of locality, the common sense idea that objects are only directly influenced by their immediate surroundings, and that no information or influence can travel faster than light. They reasoned that if measuring one particle instantly forces its distant partner into a specific state, it implies some hidden signal is flying between them, violating the cosmic speed limit set by Einstein's own theory of relativity. They concluded that there must be some hidden variables, some yet unknown properties that predetermine the particle's behavior, making the seemingly random outcomes of quantum mechanics merely an illusion of our ignorance. For decades, this remained a philosophical debate. Then, in the 1960s, physicist John Bell devised a practical way to test it. Bell's theorem provided a mathematical framework for an experiment that could distinguish between Einstein's hidden variables and the spooky reality of true quantum entanglement. The crux of the test is a statistical check. If hidden variables are at work, the correlation between measurements on the two particles would fall within a certain limit. If quantum mechanics is correct and the connection is truly non-local, the correlations would exceed that limit. When these experiments were finally conducted with increasing precision, the results were crystal clear. The quantum particles violated Bell's inequality every single time. There are no hidden variables. The spooky action is real. This non-locality is not a signal in any traditional sense. No energy or information we can control is being transmitted. Instead, it's as if the two particles are not two separate entities at all, but remain a single, unified system regardless of the physical distance between them. The universe, at its most fundamental level, is deeply interconnected in ways that render our classical notions of space and time almost irrelevant. This isn't just a theoretical curiosity. It is the foundation for emerging technologies like quantum computing and quantum cryptography. By leveraging this intimate link between particles, we can create communication networks that are fundamentally secure from eavesdropping, as any attempt to intercept the message would instantly break the delicate entangled state and alert the users. The universe, it seems, has built-in encryption based on this most mysterious of connections. Now, if quantum entanglement reveals a universe deeply interconnected in ways that defy distance, the next force answers a question so fundamental we rarely even think to ask it: why does anything have mass at all? What gives substance to the building blocks of reality, allowing them to form atoms, planets, and us? The answer lies not in a force we can touch, but in an invisible, cosmic molasses that permeates every corner of the universe, the Higgs field. This isn't a field like a magnetic field you can map with iron filings. Instead, think of it as a constant, invisible energy presence that fills what we perceive as empty space, a fundamental property of the vacuum itself. Without this field, our universe would be a radically different and utterly lifeless place. Fundamental particles like electrons and quarks would zip through the cosmos at the speed of light, never slowing down enough to bind together and form the atoms that constitute matter. There would be no stars, no planets, no chemistry, and certainly no life. The Higgs field is what gives these elementary particles their mass, effectively slowing them down and allowing them to combine. The mechanism for this is both elegant and strange, often compared to a celebrity moving through a crowded room. Imagine a famous person trying to cross a space filled with admirers. As they move, people gather around, cling to them, and slow their progress. Their interaction with the crowd gives them a kind of social mass, making them harder to accelerate. In this analogy, the celebrity is a fundamental particle and the crowd is the Higgs field. The more a particle interacts with this field, the more mass it acquires. An electron interacts only a little, so it's very light. A top quark interacts a tremendous amount, making it incredibly heavy. The particle that confirmed this cosmic mechanism, the Higgs boson, is not the field itself, but rather a tiny, localized ripple within it. Detecting this ripple required one of the most ambitious scientific experiments in human history, the Large Hadron Collider at CERN. Deep underground on the border of France and Switzerland, physicists accelerate protons to within a fraction of the speed of light and then smash them together head-on inside colossal detectors. These collisions concentrate an immense amount of energy into a microscopic space, momentarily shaking the Higgs field like striking a silent bell to make it ring, and briefly bringing a Higgs boson into existence. This particle is fantastically unstable and decays into more common particles in a fraction of a nanosecond. The proof of its creation isn't a direct photograph, but rather a painstaking statistical analysis of the telltale shower of debris left behind from billions upon billions of these violent collisions. It was from this subatomic fireworks display that scientists finally announced the discovery of the Higgs boson in 2012, a monumental triumph that confirmed a theory nearly 50 years in the making. This discovery cemented our understanding that mass is not an inherent property. A particle has no mass on its own. Instead, mass is something it acquires by moving through and interacting with the universal Higgs field. The substance of our reality, the very weight of our bodies, is granted by an invisible cosmic presence, a silent partner in existence that endows the universe with the gift of form and structure. But the existence of the Higgs field and the quantum vacuum raises a monumental question about our cosmic beginnings. If all of space is filled with these energetic fields, how did the universe grow from a microscopic point to its vast, breathtakingly uniform state in what seems like an instant? To answer this, we must rewind the clock to the very first fraction of a second after the Big Bang, to a period of unimaginable expansion known as cosmic inflation. This was not the steady, dark energy-driven expansion we see today, but a hyperactive, exponential stretching of spacetime itself, a primordial push that set the stage for everything to come. For decades, cosmologists were puzzled by several features of our universe that the standard Big Bang model couldn't explain. Why does the universe appear so strikingly uniform in every direction we look? The temperature of the cosmic microwave background radiation, the ancient afterglow of the Big Bang, is the same to 1 part in 100,000, whether we point our telescopes east, west, north, or south. This presented a horizon problem. In the standard model, there hasn't been enough time since the beginning of the universe for light or heat to have traveled between these distant regions to even them out. It's as if you walked into a vast room where hundreds of people you've never met all independently decided to wear the exact same outfit and maintain the exact same body temperature without ever communicating. The odds are astronomically impossible. Another puzzle was the universe's startling flatness. The density of matter and energy in the cosmos appears to be perfectly balanced or flat on the largest scales. If there were even a tiny bit more matter, gravity would have caused the universe to collapse back on itself eons ago. A tiny bit less, and everything would have flown apart so rapidly that galaxies could never have formed. This precise knife-edge balance seemed like an incredible coincidence with no explanation. The theory of cosmic inflation, first proposed by physicist Alan Guth in the 1980s, elegantly solves these puzzles in one grand sweep. The idea is that a mysterious form of energy, akin to a supercharged version of the Higgs field, caused the universe to inflate by a factor of at least 10 to the 78th power in less than a trillionth of a trillionth of a trillionth of a second. This incredible burst of growth is what ironed out the universe. Imagine taking a tiny, crumpled and wrinkled piece of paper, a sheet representing the primordial cosmos, full of random temperature and density fluctuations. Now inflate that paper to the size of the entire observable universe. All those wrinkles and crumples would be stretched out into near-perfect smoothness, explaining the incredible uniformity we see. It also explains the flatness. Inflating a curved space to such an enormous degree makes it appear flat, just as the surface of our planet seems flat to us standing on it, even though it is actually a sphere. The expansion was so violent and exponential that it took the initial microscopic quantum jitter from the vacuum and stretched those tiny fluctuations across the entire cosmos. These minuscule ripples in density became the gravitational seeds around which all future structure galaxies, clusters, and superclusters would eventually form. The largest structures we see today are therefore the magnified fossils of quantum noise from the universe's first moment. The most compelling evidence for this incredible event is etched into the sky. The Planck satellite and other observatories have mapped the cosmic microwave background with exquisite precision, and the pattern of temperature variations matches the predictions of inflationary theory exactly. The statistics of the hot and cold spots, their size distribution, and their correlations are a perfect fingerprint of a universe that underwent a rapid, exponential inflationary phase. This primordial push was the single most important event in the history of the cosmos after the Big Bang itself. It was the moment the universe was ironed smooth, gifted with its flat geometry, and imprinted with the blueprint for all future cosmic architecture, a one-time event whose echo we can still read in the ancient light that fills the void. But as cosmic inflation smoothed the canvas of the universe and set the stage for structure, a different kind of messenger was being forged in the hearts of the first stars, a ghostly particle that would later provide a profound window into the most violent cosmic events. These are neutrinos, and their bizarre behavior presents us with the captivating mystery of neutrino oscillation. To understand just how elusive these particles are, consider this. Trillions of them are passing through your body every single second, moving at nearly the speed of light, and the vast majority will travel through the entire Earth without interacting with a single atom. They are the phantoms of the particle world, born from the nuclear furnaces that power stars and the cataclysmic explosions that end them. Their story begins with a puzzle at the very heart of our sun. In the 1960s, an experiment deep in a South Dakota gold mine, led by physicist Raymond Davis Jr., set out to count the number of neutrinos arriving from the sun. The theory was clear: the sun's energy comes from fusing hydrogen into helium, a process that should release a specific number of electron neutrinos. Davis's detector, a massive tank filled with 615 tons of dry cleaning fluid, was designed to catch these ghosts. When a neutrino struck a chlorine atom, it would transform it into a radioactive argon atom, which could then be painstakingly counted. The results, however, were baffling. He was detecting only about 1/3 of the predicted number of solar neutrinos. For decades, this solar neutrino problem remained a major conundrum. Was our understanding of the sun's nuclear core wrong, or was something strange happening to the neutrinos on their journey? The answer turned out to be one of the most astonishing discoveries in modern physics. Neutrinos weren't disappearing, they were changing identities. The standard model of particle physics had long assumed that neutrinos were massless, and if that were true, their identity would be fixed forever. An electron neutrino would always remain an electron neutrino, but the solution to the solar neutrino problem revealed this was false. We now know that neutrinos do have a tiny, almost imperceptible amount of mass, and this allows them to oscillate, to morph from one type or flavor to another as they travel through space. An electron neutrino produced in the sun's core can transform into a muon neutrino or a tau neutrino by the time it reaches Earth, and Davis's experiment was only sensitive to electron neutrinos, missing the ones that had changed form. Confirming this required incredibly sophisticated detectors. Modern experiments like Super Kamiok and in Japan use colossal tanks of ultra-pure water, buried deep underground to shield them from other radiation. When a neutrino happens to interact with a water molecule, it can create a faint flash of light called Cherenkov radiation, a distinctive blue glow that reveals not only the neutrino's presence but also its flavor and the direction it came from. Another detector, the Sudbury Neutrino Observatory in Canada, used heavy water to be sensitive to all three neutrino types equally. Its data provided the definitive proof, showing that the total number of neutrinos arriving from the sun matched predictions perfectly. They had simply been playing a game of cosmic hide and seek, changing their identities in mid-flight. This ability to oscillate makes them incredible cosmic messengers. Because they so rarely interact, they can travel in a straight line from their source, carrying pristine information about the environment where they were born. The most dramatic demonstration of this came in 1987, when a supernova exploded in the Large Magellanic Cloud, a neighboring galaxy. Hours before the visible light from the blast reached Earth, 3 neutrino observatories around the world detected a burst of 24 neutrinos. these particles had streamed directly out of the collapsing stellar core, unimpeded by the outer layers of the star, giving astronomers a direct look at the very moment a star's heart was forming a neutron star or black hole. They are our only direct probe into the intense heart of a supernova. Today, huge international projects like the Ice Cube Neutrino Observatory are pushing this even further. At the South Pole, they have embedded thousands of sensitive light detectors deep within a cubic kilometer of pristine ice, turning a massive volume of the Antarctic glacier into the world's largest particle detector. They are now mapping the neutrino sky, searching for these ghosts that originate not from our Sun, but from supermassive black holes in distant galaxies and other extreme astrophysical phenomena. Each detection is like opening a letter sent from the most powerful engines in the universe, written in a code of oscillation that we are only just beginning to decipher. Yet for all the ghostly subtlety of neutrinos, some of the most profound cosmic mysteries may be solved by a particle that, as far as we know, doesn't even exist. This brings us to one of the most tantalizing missing pieces in all of theoretical physics, the search for the magnetic monopole. We are all intimately familiar with magnets. Every child knows that a bar magnet has a north pole and a south pole. If you break that magnet in half, you don't get an isolated north and an isolated south. Instead, you get two smaller magnets, each with its own pair of poles. This is a fundamental rule of electromagnetism as we understand it. Magnetic poles always come in pairs. There are no single, isolated magnetic charges, or so it seems. But what if that weren't true? What if a particle existed that carried just a single magnetic charge, a north pole without a south, or vice versa? This hypothetical particle is the magnetic monopole, and its potential existence was first seriously proposed by physicist Paul Dirac in 1931. Dirac wasn't just playing with ideas, he was trying to solve a deep puzzle. Why is electric charge quantized? In our universe, every charged particle has a charge that is an exact multiple of the electron's charge. Why are there no particles with 1/3 or 1/2 of that charge? Dirac demonstrated mathematically that if even a single magnetic monopole existed somewhere in the universe, it would immediately explain this quantization. The very presence of a monopole would force electric charges to come in discrete, quantized units, as if the universe's accounting system required whole numbers. It was an elegant and powerful idea, linking the nature of electricity and magnetism in a beautifully symmetrical way. The case for monopoles grew even stronger with the development of grand unified theories, or GUT, in the 1970s. These theories attempt to describe a period in the very early universe when the three fundamental non-gravitational forces, the electromagnetic force, the strong nuclear force, and the weak nuclear force, were unified into a single superforce. These theories predict that as the hot, young universe expanded and cooled, it underwent a series of phase transitions, much like water freezing into ice. And according to many GOTs, these cosmic phase transitions should have created topological defects in the fabric of spacetime itself. Among these defects would be incredibly massive and stable particles, magnetic monopoles. Their predicted mass is almost unimaginable, perhaps as heavy as an entire bacterium crammed into a single subatomic particle, making them billions upon billions of times more massive than a proton. This created a huge problem for cosmology, famously known as the monopole problem. If grand unified theories are correct, the early universe should have been flooded with these monstrously heavy relics. They would be so numerous and so massive that they would have overwhelmed the density of the universe, causing it to recollapse long before any stars or galaxies could ever form. The fact that our universe is old, vast, and filled with structure implies that these monopoles are nowhere to be found. Their glaring absence was one of the key motivations for the theory of cosmic inflation we discussed earlier. That incredible burst of expansion would have diluted the monopole density to virtually zero, sweeping them so far beyond our observable horizon that finding one becomes astronomically improbable. Inflation saved the theory, but in doing so, it made the monopoles detection incredibly difficult. This has not stopped physicists from looking. The hunt for magnetic monopoles has been going on for decades, using some of the most ingenious experiments ever devised. Because a monopole would be so massive, it would punch through matter with ease, leaving a unique and detectable trail. Some experiments involve running large loops of superconducting wire called squid, which are exquisitely sensitive to magnetic fields. The passage of a single magnetic charge through such a loop would induce a distinct, persistent current, a permanent, smoking gun signal that couldn't be created by any other known particle. Other searchers have scoured moon rock and material from the ocean floor, hoping to find a monopole that was trapped in the material eons ago. There was even a famous, fleeting event in 1982 when a detector at Stanford University recorded a signal that perfectly matched what a monopole would produce. The event, known as the Valentine's Day Monopole Candidate, caused tremendous excitement, but it was never repeated. To this day, it remains an intriguing but unverified anomaly. The enduring search for this elusive particle is about far more than just completing a collection. Discovering a magnetic monopole would be a revolutionary moment in physics, providing direct evidence for physics at unimaginably high energy scales and confirming that the fundamental forces of nature were once united. It would be a window into the universe's first moments, a relic from a time of perfect symmetry, and a testament to the power of human curiosity to probe the deepest layers of cosmic reality, even for something that might not be there. Now, from the search for a particle that might not exist, we turn our attention to a phenomenon that demonstrably does, one that defies the very rules of classical physics and is absolutely essential for our existence. This is the bizarre reality of quantum tunneling, a process where particles perform what can only be described as the ultimate magic trick, passing straight through solid barriers as if they weren't even there. In our everyday world, this is impossible. If you throw a tennis ball at a brick wall, it will always bounce back. It simply doesn't have the energy to go through the wall. Classical physics tells us that to get to the other side of an energy barrier, you must have at least enough energy to go over it, but in the quantum realm, the rules are different. Here, particles like electrons and protons are not just tiny balls, they are also probability waves spread out and fuzzy. This wave-like nature means a particle's exact location is not a single point but a cloud of potentiality, a set of odds describing where it might be found. And this cloud of probability doesn't just stop abruptly at a barrier, it decays exponentially inside it, but it never quite reaches zero. There is always a minuscule but non-zero chance that the particle will be found on the other side of the barrier. It doesn't bore through it, it effectively cheats, skipping the impossible climb by appearing where its probability wave allows it to be. This isn't just a theoretical curiosity, it is the reason our sun shines. At the core of a star, protons need to collide and fuse together to create helium and release energy. But there's a problem. Protons are all positively charged, and they fiercely repel each other due to the electromagnetic force. The energy required to overcome this repulsive force and push two protons close enough to fuse is tremendous, far higher than the average energy of protons even in the sun's intensely hot core. Classically, the sun shouldn't shine at all. Quantum tunneling is the solution. Because each proton has a probability wave, there's a tiny chance that it can tunnel through the electromagnetic repulsion barrier, instantly finding itself close enough to its partner for the strong nuclear force to take over and bind them together. This process is incredibly rare for any single pair of protons, but the sun has so many protons in its core that this rare event happens countless times every second, providing the steady, life-giving fusion that powers our star and virtually every other star in the universe. Without quantum tunneling, the cosmos would be dark and cold. This same principle is harnessed in the very technology you might be using right now. The transistors that form the backbone of all modern electronics rely on a phenomenon called electron tunneling. In a type of memory known as flash memory, which is used in USB drives, smartphones, and solid-state drives, information is stored as tiny electrical charges. To write a 1 or a 0, electrons must be moved onto a microscopic floating gate, which is electrically isolated by a very thin insulating layer. This layer is a barrier that electrons classically shouldn't be able to cross, but because the layer is so incredibly thin, the probability wave of an electron can extend right through it. By applying a voltage, we can make it probable that electrons will tunnel through this insulator, effectively teleporting charge onto the gate to store data. This same tunneling effect is also what limits how small we can make these transistors, as it becomes a source of leakage current, a constant reminder that quantum mechanics ultimately dictates the limits of our technology. Perhaps the most stunning practical application of this effect is the scanning tunneling microscope, or STM. This remarkable invention earned its creators the Nobel Prize and allows scientists to actually see and manipulate individual atoms. How does it work? A needle with an atomically sharp tip is brought incredibly close to a surface but not touching it. Just a nanometer away, a voltage is applied between the tip and the surface. According to classical physics, with no physical contact, no current should flow. But thanks to quantum tunneling, the electrons see the tiny gap not as a barrier but as a tunnel. A tunneling current flows across the gap, and the strength of this current is exquisitely sensitive to the distance. By maintaining a constant current, the tip moves up and down, precisely tracing the hills and valleys of the atomic landscape below it. This allows the instrument to create breathtakingly detailed, three-dimensional maps of surfaces at the atomic level, literally allowing us to visualize the building blocks of matter. Finally, quantum tunneling is the driving force behind one of the most fundamental processes that shapes elements, radioactive decay. In certain unstable atomic nuclei, a pair of protons and neutrons can form an alpha particle, essentially a helium nucleus. This particle is held inside the nucleus by the strong nuclear force, which acts like a deep, narrow well. Surrounding this well is the repulsive electromagnetic force from all the other protons, creating a tall energy barrier. Classically, the alpha particle is trapped. It doesn't have enough energy to get out, but quantum mechanically, its probability wave has a small tail that extends beyond the barrier. There is a small probability that the alpha particle will spontaneously tunnel out of the nucleus each second. This is why radioactive elements have half-lives, the time it takes for half of a sample to decay. For some elements, the tunneling probability is high and the half-life is short. For others, like uranium-238, the barrier is wider and more difficult to tunnel through, resulting in a half-life of over 4 billion years. The very stability of matter itself is governed by the odds of this quantum escape act. While quantum tunneling allows particles to cheat their way through barriers on the smallest scales, the most dramatic distortions of reality occur when the very fabric of space-time is violently shaken by the most massive objects in the universe. This brings us to a phenomenon that once existed only in theory, a direct prediction of Einstein's general relativity that took a century to confirm: gravitational waves. Imagine the cosmos not as a static stage, but as a vast, flexible fabric, the four-dimensional continuum of spacetime. According to Einstein, mass and energy tell this fabric how to curve, and that curvature tells objects how to move, which we experience as gravity. But what happens when truly massive objects accelerate? They don't just bend the fabric, they send ripples racing outward across the cosmos at the speed of light, like waves spreading across the surface of a pond after a stone is dropped in. These ripples are gravitational waves, and they are incredibly faint. The distortion they cause is almost unimaginably small. A passing gravitational wave from a distant cosmic event would cause the entire solar system to very slightly stretch and squeeze. The distance between the Sun and Earth might change by the width of a single atom. Detecting such a minuscule signal seemed like an impossible dream for decades. That dream became reality in September 2015, when the twin detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history. Each LIGO observatory consists of two 4-kilometer-long vacuum tubes arranged in an L shape. A laser beam is split and sent down each arm, bouncing off mirrors to travel back and recombine. In perfectly calm spacetime, the light waves return and cancel each other out. But if a gravitational wave passes through, it will very slightly distort spacetime, making one arm fractionally longer and the other shorter for a fleeting instant. This changes the distance the lasers travel, so they no longer cancel out perfectly, creating a tiny flicker of light at the detector, a signature of the wave. The first signal ever detected was designated GW150914, named for the date it was observed. The data showed a characteristic chirp, a rising frequency, and amplitude that perfectly matched the predictions for the final moments of a binary black hole merger. Over 1 billion light-years away, two black holes, one about 36 times the mass of the Sun and the other 29, had been locked in a mutual orbit, slowly losing energy by radiating gravitational waves. As they spiraled closer together, their speed increased, and the gravitational waves they emitted grew stronger and higher in pitch. In a final, violent fraction of a second, they reached nearly half the speed of light and merged into a single, more massive black hole. In that collision, an amount of energy equivalent to about 3 times the mass of the Sun was converted directly into gravitational waves and blasted across the universe. This was the event that shook LIGO mirrors, confirming Einstein's prediction and opening an entirely new window on the cosmos. Since that first detection, the field of gravitational wave astronomy has exploded. We have now heard the cosmic collisions of numerous black hole pairs, but perhaps the most scientifically rich event came in August 2017. This time, the observatories detected a signal that was both seen and heard. The event, GW170817, was the collision of two neutron stars. Unlike black holes, which merge in darkness, neutron star collisions are incredibly violent and bright, producing a firework display across the electromagnetic spectrum. The gravitational wave signal provided the early alert, and within seconds, telescopes around the world and in space swiveled to look at the patch of sky it came from. What they witnessed was a kilonova, a massive explosion that forged heavy elements like gold, platinum, and uranium and spewed them out into the cosmos. In a very real sense, that single observation told us that the gold in a wedding ring or the uranium in a power plant was likely created in the apocalyptic collision of two dead stars, an event whose ripples in space-time we can now trace. Each new detection adds to our understanding of these extreme objects. The ring-down signal after a black hole merger allows us to test the no-hair theorem, which suggests black holes are described only by their mass, spin, and electric charge. The vibrations of the newly formed black hole are like striking a bell. The tone and decay of the sound tell us about the bell's structure. Gravitational waves are also our most direct probe of neutron stars, whose interior composition remains a mystery. The way they deform each other before merging reveals how stiff or fluid their ultra-dense nuclear matter is under incredible pressure. With every ripple we detect, we are not just listening to the stories of cosmic crashes. We are reading the very signature of spacetime itself, learning how it behaves under the most extreme conditions imaginable. While gravitational waves ripple across the fabric of spacetime from cataclysmic events, the universe may also be etched with permanent, primordial scars from its very first moments, cosmic scars that take the form of unimaginably thin, unimaginably dense flaws in reality itself. These are cosmic strings, theoretical one-dimensional defects that might have been forged in the fiery chaos of the early universe, and if they exist, they would be some of the most bizarre and dramatic structures in all of cosmology. To understand how such an object could form, we need to think about phase transitions. We see phase transitions all the time in everyday life, like when water cools and freezes into ice. As the water freezes, the molecules arrange themselves into a very specific, orderly crystal structure. But this process isn't always perfect. If the water freezes very quickly, defects can form in the ice, tiny cracks, air bubbles, or lines where different crystal domains met and didn't align perfectly. The early universe underwent a series of similar but far more dramatic phase transitions as it expanded and cooled from an incredibly hot, dense state. According to many grand unified theories, the fundamental forces we see today, electromagnetism and the nuclear forces, were once unified as a single superforce. As the universe cooled, this symmetry was broken and the forces split off from one another. It's during these cosmic scale, freezing events that topological defects could have formed, and cosmic strings are one specific type of these defects. A cosmic string would be a flaw in the very geometry of spacetime, a tiny, crack-like region where the primordial high-energy state of the universe became trapped, unable to cool down with the space around it. Imagine spacetime as a flat sheet. Normally, that sheet is smooth, but a cosmic string would be like taking a narrow wedge out of that sheet and then taping the edges back together. The surface still looks flat, but if you draw a circle around the point where the tip of the wedge was, you'll discover that the circle encompasses more than 360 degrees. This is the gravitational signature of a string. It creates a deficit angle in space. It wouldn't have a gravitational pull in the Newtonian sense. You wouldn't get pulled toward it. Instead, it would warp space around it so that two light beams passing on opposite sides of the string would be bent, not toward each other, but in a way that would make them miss each other. If a cosmic string passed between you and a distant galaxy, you might actually see two identical images of that galaxy, a phenomenon called gravitational lensing, but with a uniquely sharp, edgy quality, unlike the smooth warping caused by a black hole or dark matter halo. The physical properties of these objects are almost beyond science fiction. A cosmic string would be narrower than a proton, but it would have an astronomical mass. Just a single kilometer of string might contain more mass than the entire Earth, pulled into that infinitesimally thin line. And because they are a fundamental flaw in space-time, they wouldn't be made of matter as we know it. You couldn't cut them or break them. They would either form infinite, perfectly straight lines, or they might form loops that oscillate at a significant fraction of the speed of light. As these loops whip through space, they would lose energy by radiating gravitational waves, a faint but continuous hum in the background of the cosmos that could be detectable by future observatories. Some theories even suggest that the oscillations of these loops could have provided the initial density perturbations that seeded the formation of the very first galaxies, meaning these cosmic defects could be the architects of the large-scale structure we see today. The hunt for evidence of cosmic strings is a major endeavor in both theoretical and observational cosmology. Astronomers meticulously search through maps of the cosmic microwave background, the ancient afterglow of the Big Bang, looking for the unique telltale patterns of sharp jumps in temperature that a moving string would imprint. They also scour the sky for pairs of distant galaxies or quasars that are identical in every way, a sign that a string might be lensing a single object into a double image. While no definitive evidence has been found yet, the search continues because the discovery of a cosmic string would be more than just finding a new astronomical object. It would be a direct glimpse into the universe a fraction of a second after its birth, confirming our theories about symmetry breaking and phase transitions at energies so high we could never hope to recreate them in a particle. Collider, they are hypothetical relics of a more ordered, symmetrical age of the cosmos, and their potential discovery would forever change our understanding of the universe's deepest architecture. But the idea of the vacuum possessing energy, as we saw with the Higgs field and dark energy, leads us to one of the most unsettling and profound possibilities in all of theoretical physics, the risk of vacuum metastability. What if the vacuum state that our universe currently occupies, the very foundation of reality that gives particles their mass and allows atoms to form, isn't the most stable state possible? What if it's a false vacuum, a precarious and temporary valley in a much larger cosmic energy landscape, and at any moment a random quantum event could cause it to tunnel into a true, lower energy vacuum, fundamentally rewriting the laws of physics in an unstoppable wave of annihilation? This concept hinges on the shape of the Higgs field's potential. Think of the state of our vacuum as a ball resting in a valley. For our universe to be truly stable, this ball should be sitting at the absolute bottom of the deepest possible valley, a true vacuum. However, the mathematics of the Standard Model, combined with the measured mass of the Higgs boson, suggests something more disquieting. Our valley might not be the deepest one. There could be a far deeper, far more stable valley elsewhere, separated from our own by a colossal energy mountain. For now, our ball is stable. It would take a tremendous amount of energy to push it over that mountain. But in the quantum world, impossible is just a matter of probability. Through the same quantum tunneling that powers the sun, there is a tiny, non-zero chance that a small region of our false vacuum could spontaneously tunnel through that barrier, creating a bubble of true vacuum. This bubble would be a region of space-time where the laws of physics are completely different. The Higgs field would have a different value, which would likely change the masses of fundamental particles and could even prevent atoms from forming as we know them. The properties that allow for chemistry and life would simply cease to exist, and this is not a local event. The moment this bubble nucleates, the laws of physics governing its expansion would cause its walls to expand outward in all directions at the speed of light. From the perspective of anything inside the bubble, the change would be instantaneous and unfathomable. From the perspective of an outside observer, they would see a sphere of new physics rushing toward them at light speed. There would be no warning, no way to see it coming, and absolutely no possibility of escape. One moment, the universe is as it is. The next, an all-consuming sphere of new physical law has rewritten everything in its path. The sheer scale of this risk is both terrifying and paradoxically reassuring. The calculated probability for such an event to occur in any given volume of space is astronomically low. Based on the current best estimates, the average time you would have to wait for a vacuum decay event to spontaneously happen in a volume the size of our observable universe is longer than the current age of the universe by many, many orders of magnitude. It is far more likely that the sun will spontaneously turn into a black hole, or that all the atoms in your body will simultaneously quantum tunnel to the other side of the galaxy. And yet the probability is not zero. The equations permit it. This means that if our universe is indeed metastable, the decay could have already been triggered somewhere else by some random quantum fluctuation in the distant past. A bubble of true vacuum could be expanding toward us right now, and we would have no way of knowing until it arrived. Yet for all the profound mysteries we've unraveled, from the quantum vacuum to the fabric of spacetime itself, there remains one monumental schism at the very heart of modern physics, a fundamental divide between our two most successful and accurate theories of reality. On one hand, we have general relativity, Einstein's magnificent description of gravity as the curvature of spacetime, which perfectly predicts the orbit of planets, the bending of light, and the existence of black holes. On the other, we have quantum mechanics, which with astonishing precision governs the behavior of atoms and subatomic particles. The problem is that these two foundational pillars of physics are fundamentally, mathematically incompatible. They speak different languages and break down completely in domains where both gravity and quantum effects are significant, such as the center of a black hole or the very first moment of the Big Bang. This great divide has launched the most ambitious intellectual quest in all of science, the search for a theory of quantum gravity. The core of the conflict lies in how each theory views reality. General relativity is a classical theory. It describes a smooth, continuous, and deterministic fabric of spacetime. Quantum mechanics, by stark contrast, is probabilistic and thrives on discrete, jittery uncertainty. The most glaring example of this incompatibility emerges when we try to describe the fabric of spacetime itself at the smallest possible scales. Quantum theory suggests that at the Planck scale, an almost inconceivably tiny distance of 10 to the minus 35 meters, the smooth geometry of spacetime predicted by relativity should dissolve into a seething, chaotic foam, a turbulent ocean of virtual black holes and wormholes blinking in and out of existence. To understand physics at this level, we need a theory that can quantize gravity, describing the force not as a smooth field, but as discrete packets of energy called gravitons. This is the ultimate goal of the unification quest. One of the most prominent and debated approaches to this problem is string theory. At its heart, string theory proposes a breathtakingly elegant shift in perspective. The fundamental constituents of the universe are not zero-dimensional point particles, but tiny, one-dimensional vibrating strings. Each different vibration mode of these strings corresponds to a different particle. One vibration gives you an electron, another a quark, and a specific, unique vibration is hypothesized to give you the graviton, the quantum carrier of gravity. This simple but profound idea automatically incorporates gravity into the quantum realm. Furthermore, string theory requires more than the three spatial dimensions we experience. For the math to work consistently, it demands extra dimensions, often 10, 11, or even 26, curled up into shapes so small that we cannot perceive them. The properties of these Calabi-Yau manifolds, as they're called, would determine the constants of nature we observe, like the mass of the electron or the strength of gravity. If proven true, string theory wouldn't just be a theory of quantum gravity, it would be a theory of everything, a single framework describing all particles and all forces. However, its critics point to a significant hurdle, a current lack of testable predictions. The energy scales required to probe these strings or uncurl the extra dimensions are far beyond the reach of any particle collider we could ever build, making experimental verification immensely challenging. Offering a radically different vision is loop quantum gravity. If string theory tries to unify all forces by adding extra dimensions, loop quantum gravity takes a more minimalist approach, focusing solely on quantizing spacetime itself. It proposes that space is not continuous, but is instead woven from a network of finite, discrete loops, a spin network. Think of the fabric of reality not as a smooth sheet, but as a tapestry made of individual threads. The area of a surface or the volume of a region isn't infinitely divisible. It comes in tiny, fundamental units, much like a digital image is made of pixels. This granular structure of space becomes apparent only at the Planck scale. One of the theory's most compelling insights is its application to the beginning of the universe and the interiors of black holes. In the standard Big Bang model, the universe emerges from a singularity, a point of infinite density where the laws of physics break down. Loop quantum gravity replaces this terrifying singularity with a big bounce, a scenario where a previous, collapsing universe rebounded into our expanding one due to quantum gravitational repulsion. Similarly, it suggests the heart of a black hole might not be a point of infinite density, but a gateway to another region of spacetime. Other compelling ideas also vie for attention in this grand quest. Causal dynamical triangulation approaches the problem by building spacetime from simple, geometric building blocks like tiny triangles and allowing them to combine according to specific rules, effectively growing the fabric of the universe from the bottom up through a process that mimics quantum evolution. As these blocks assemble, the familiar four-dimensional spacetime of our daily experience emerges naturally from the chaos, a property known as dimensional emergence. Meanwhile, some physicists explore the possibility that gravity isn't a fundamental force at all. The holographic principle, inspired by the physics of black holes, suggests that our three-dimensional universe might actually be a projection of information encoded on a distant two-dimensional surface, much like a hologram. If true, this would mean the world we perceive is a kind of illusion, and that the true laws of physics are simpler and lower-dimensional. The implications of successfully unifying gravity with quantum mechanics are almost beyond imagination. It would allow us to peer beyond the veil of the Big Bang singularity and understand the true origin of our cosmos. It could reveal the ultimate fate of information that falls into a black hole, resolving the famous information paradox and telling us whether information is truly lost forever, which would violate a core tenet of quantum mechanics. It might even provide insights into the nature of dark energy and dark matter, the two greatest mysteries in modern cosmology. Most profoundly, a complete theory of quantum gravity would represent a culmination of humanity's centuries-long endeavor to understand the fundamental laws governing existence, revealing a universe that is, at its core, coherent, mathematical, and perhaps even comprehensible. The quest continues, a testament to our unyielding desire to find a single, harmonious story that explains everything from the smallest quanta to the largest cosmic structures. While the hunt for magnetic monopoles continues, another hypothetical particle has captured the imagination of physicists for a different set of compelling reasons, one that could solve two of the most perplexing puzzles in science with a single, elegant idea. This is the action, a hypothetical ultralight particle that is a prime candidate to explain the nature of dark matter, while simultaneously resolving a deep mystery in the laws of physics known as the strong CP problem. To understand why this particle is so alluring, we must first venture into the bizarre world of the strong nuclear force, the incredibly powerful glue that holds the protons and neutrons in every atom's nucleus together. The strong force is described by a theory called quantum chromodynamics, and it possesses a surprising symmetry. The equations that govern it should allow for a certain kind of violation of charge and parity symmetry, a process that would leave a distinct experimental signature. This is known as the strong CP problem. In practical terms, this violation should cause the neutron, which is electrically neutral, to possess a small but measurable electric dipole moment, a sort of internal separation of positive and negative charge that would make it act like a tiny compass needle. Our most sensitive experiments have searched for this neutron dipole moment, and they have found nothing. The neutron's electric dipole moment is so incredibly small that it appears this CP violation is mysteriously absent from the strong interaction. The universe seems to be fine-tuned in a way that prevents it, and physicists deeply dislike unexplained fine-tuning. In the late 1970s, physicists Roberto Pexi and Helen Quinn proposed a brilliant solution. They suggested that this fine-tuning isn't a coincidence but is actually the result of a new, fundamental symmetry in nature. Shortly after, Frank Wilczek and Steven Weinberg realized that breaking this symmetry would produce a new, very light, very weakly interacting particle. The action, named after a brand of laundry detergent for its ability to clean up the problem. The action would effectively act as a cosmic adjustment knob, dynamically tuning the strong interaction to eliminate the CP violation and explaining why the neutron's electric dipole moment is undetectably small. This alone would have been a major theoretical triumph, but the action had another, even more spectacular property that would soon make it a superstar in cosmology. It is a perfect candidate for dark matter. The properties required for the action to solve the strong CP problem almost exactly match those needed for a type of dark matter known as cold dark matter. It would be electrically neutral, incredibly light, potentially billions of times lighter than an electron, and it would interact with ordinary matter only extremely weakly via gravity and through rare interactions with electromagnetic fields. Most importantly, actions would have been produced in colossal numbers in the hot, early universe, not from particle decays, but through a mechanism akin to a cosmic field settling into its lowest energy state. As this field oscillated, it would have flooded the cosmos with a cold, coherent wave of actions, providing exactly the kind of invisible, non-luminous mass that forms the gravitational scaffolding for galaxies. This two-for-one solution, solving a major particle physics puzzle and explaining the dominant form of matter in the universe, is what makes the action such an elegant and compelling idea. What truly sets actions apart from other dark matter candidates like WIMP is their uniquely quantum behavior on a macroscopic scale. Because they are so incredibly light and were born from a coherent field, they wouldn't behave like a swarm of individual particles. Instead, vast collections of actions would act more like a single, pervasive wave undulating throughout the galaxy. This wave-like nature means that actionic dark matter wouldn't be clumpy. It would form a smooth, oscillating background field that permeates every corner of the galaxy, including the room you're in right now. The frequency of this oscillation is directly tied to the action's mass, and detecting this faint, universal hum is the central goal of a new generation of incredibly sensitive experiments. The most promising technique for listening to this hum is known as the action haloscope, a concept pioneered by physicist Pierre Sicavy. The principle is ingenious yet straightforward. In a powerful magnetic field, actions should have a tiny probability of converting into microwave photons. A haloscope is essentially a tunable microwave radio receiver housed inside a strong magnet. The experiment involves cooling a metal cavity to near absolute zero to eliminate thermal noise, placing it in the bore of a large superconducting magnet, and then listening very carefully across a range of microwave frequencies. The idea is to slowly tune the cavity, much like turning the dial on an old-fashioned radio, and listen for a faint, monochromatic signal, the telltale whine of actions converting into photons at one specific frequency. If the cavity's resonant frequency matches the frequency of the action field's oscillation, the signal would be dramatically amplified, revealing the presence of dark matter. These experiments, like the Action Dark Matter Experiment or ADMX, represent a monumental technical challenge. They are searching for a signal so weak it is utterly drowned out by the natural noise of the universe. To put it in perspective, the expected signal from galactic actions is comparable to the radio noise emitted by a single transistor, while the experiment itself is the size of a large piece of equipment. The quest demands immense magnetic fields, exquisitely sensitive quantum amplifiers, and temperatures colder than deep space. Despite these challenges, the search is progressing rapidly, scanning through the possible mass ranges with increasing sensitivity. The discovery of an action would be a watershed moment in science, simultaneously revealing the identity of dark matter and providing a profound window into the symmetries that shape the laws of physics in the universe's first moments. It would show that the answers to our biggest questions are not only out there but are woven into the very fabric of reality, oscillating silently all around us, just waiting for the right instrument to finally hear their faint cosmic song. Perhaps the most direct and astonishing evidence that empty space is anything but empty comes from a subtle yet measurable force that emerges from the quantum vacuum itself. This is the Casimir effect, a remarkable phenomenon where the sheer nothingness between two objects can actually push them together. To see it in action, imagine taking two perfectly smooth, uncharged metal plates and placing them in a perfect vacuum, so close that they are only a few hundred nanometers apart, a distance smaller than the wavelength of visible light. In our classical, everyday view of the world, absolutely nothing should happen. There's no gravity, no magnetism, no electric charge at work, And yet, if you could observe this experiment with incredible precision, you would see the plates gently pull toward each other as if by an invisible hand. That hand is the quantum vacuum, and it is anything but passive. The explanation for this bizarre force lies in the very nature of the quantum foam we discussed earlier. Remember that virtual particles are constantly flashing in and out of existence, borrowing energy from the universe for a fleeting moment. These particles aren't just random, they manifest as waves of all possible wavelengths. Now think about the space between the two plates versus the space outside them. In the vast open space outside, virtual particles of all wavelengths can pop into being. But in the narrow gap between the plates, only certain wavelengths can fit. It's like the difference between the open ocean, where waves of all sizes can roll freely, and a narrow canal where only waves of a specific size that perfectly match the width of the canal can exist. This restriction means there are actually fewer virtual particles and energy fluctuations between the plates than there are in the unrestricted space outside. With a lower energy density inside the gap and a higher energy density outside, the result is a net inward pressure that pushes the plates together. The vacuum outside is literally more energetic and robust than the vacuum squeezed between the plates, and this imbalance creates a measurable force. This prediction was first made by Dutch physicist Hendrik Casimir in 1948, and it took nearly half a century for technology to advance enough to measure it with definitive accuracy. In 1997, at the University of Washington, Steve Lamoureux conducted an exquisitely delicate experiment that confirmed the Casimir force with a precision of within 1% of Casimir's original prediction. It was a monumental moment, providing the first direct laboratory-scale proof that the quantum vacuum is a real, dynamic entity with tangible physical effects. The implications of this discovery stretch far beyond a fascinating laboratory curiosity. For the field of nanotechnology, where engineers build machines and circuits on the scale of molecules, the Casimir force is a formidable and often frustrating obstacle. As the components of a nano device are shrunk to separations of mere nanometers, this vacuum pressure becomes a dominant force. It can cause tiny, movable parts to spontaneously stick together, a phenomenon known as stiction, which can wreck delicate machinery. Understanding and accounting for the Casimir effect is now absolutely essential for designing viable nanoscale devices, from optical switches to the next generation of computer chips. Researchers are even exploring ways to harness this force, perhaps by engineering materials with specific magnetic properties to create a repulsive Casimir effect that could prevent components from sticking, turning a quantum nuisance into a useful tool. On a far grander scale, the Casimir effect provides a powerful clue for one of the most perplexing problems in all of cosmology: the nature of dark energy. You'll recall that dark energy is the mysterious force causing the accelerated expansion of the universe, and one theory suggests it could be a manifestation of the vacuum energy, the energy of virtual particles themselves. When physicists try to calculate the strength of this vacuum energy based on quantum theory, they run into a shocking problem. Their calculations suggest a value for the vacuum energy density that is around 120 orders of magnitude. That's a 1 followed by 120 zeros larger than what we observe from the measured effects of dark energy. This is arguably the worst prediction in the history of science. The fact that the Casimir force, a local manifestation of vacuum energy, can be so precisely measured, and yet the large-scale cosmological effect remains so inexplicably weak, is a central paradox of modern physics. It tells us that while we have confirmed the reality of the quantum vacuum, we are still profoundly missing a deeper understanding of how its energy truly works, a mystery that continues to challenge our most brilliant minds. Yet for all the forces that hold the universe together, perhaps the most profound mystery of all is why we are here to observe it in the first place. According to everything we know about particle physics, the Big Bang should have created equal amounts of matter and antimatter. And when matter and antimatter meet, they annihilate each other in a flash of pure energy. So the cosmos should have swiftly self-destructed, leaving behind nothing but a thin, expanding sea of radiation. The fact that we live in a universe filled with galaxies, stars, planets, and life is undeniable proof that this did not happen. Somehow, for every billion pairs of matter and antimatter particles that annihilated in the early universe, a single matter particle was left over. This tiny 1 in a billion imbalance is known as the Barrian asymmetry, and it is the reason anything made of atoms exists at all. To understand how baffling this is, we need to look at the concept of symmetry in physics. Many of the laws of the universe are symmetric, meaning they work the same way if you reverse certain conditions. For a long time, physicists believed that if you swapped every particle with its antiparticle, a process called charge conjugation C, and then viewed the interaction in a mirror which reverses spatial coordinates or parity P, the laws of physics would remain unchanged. This is known as CP symmetry. If this symmetry were perfect, the universe would have no preference for matter over antimatter, and the Big Bang would have produced them in exactly equal numbers, leading to total annihilation. The discovery that this symmetry is violated was the first crucial clue that the universe might actually favor matter. This violation was first observed in a stunning experiment in 1964. Physicists James Cronin and Val Fitch were studying the decay of neutral K mesons or kaons, which are particles that can oscillate between matter and antimatter states. They found that the matter and antimatter versions of these particles decayed at slightly different rates. This tiny difference in behavior proved that the universe, on a fundamental level, does treat matter and antimatter entirely equally. This CP violation was a monumental discovery that earned them the Nobel Prize, as it provided a potential mechanism for creating the matter-antimatter imbalance. However, there was a problem. The amount of CP violation observed in kaon decays and later in other particles is far too small to account for the vast dominance of matter we see in the cosmos. It's like finding a single penny when you need $1 million. It's the right currency, but the amount is woefully insufficient. This gap between the observed effect and what's needed to save the universe has led physicists to propose a dramatic event in the cosmos's early history, electroweak baryogenesis. This theory suggests that the imbalance was forged during a critical phase transition when the universe was just a trillionth of a second old. At this incredibly young age, the universe was still so unfathomably hot that the electromagnetic force and the weak nuclear force were unified into a single electroweak force. As the universe expanded and cooled, it underwent a phase change, much like water freezing into ice, and these two forces separated. Theorists propose that this phase transition could have been the catalyst. If it occurred in a specific, not quite even way, creating bubbles of the new phase that expanded and collided, it could have created the right conditions for the known CP violation to act like a cosmic filter. Processes involving hypothetical heavy particles could have preferentially produced matter over antimatter, scattering the leftover matter particles into the expanding universe before they could find partners to annihilate with. While the electroweak epoch is a leading candidate, it is not the only game in town. Other theories look to even earlier times or more exotic physics. Leptogenesis, for example, suggests that the imbalance might have started not with quarks, which make up protons and neutrons, but with leptons, the family of particles that includes electrons and neutrinos. In this scenario, heavy, right-handed neutrinos, which are predicted by some theories but have not yet been discovered, would have decayed asymmetrically in the very early universe, producing a slight excess of matter leptons. This lepton asymmetry could then have been converted into a baryon asymmetry through subtle Sphaleron processes, which are interactions that can change lepton number into baryon number. This elegant idea directly ties the mystery of matter's dominance to another great puzzle, the profound nature of neutrinos and their tiny masses. The search for answers is now a three-pronged assault involving particle colliders, cosmic observations, and profound theoretical work. Experiments at the Large Hadron Collider are trying to recreate the conditions of the electroweak phase transition, searching for any sign of new particles or additional sources of CP violation that could tip the scales. Meanwhile, astronomers are looking for the faintest echoes of this primordial discrimination. If baryogenesis happened, it might have generated a background of gravitational waves with a specific frequency that next-generation observatories in space could potentially detect. And deep underground, incredibly sensitive experiments are looking for the ultimate smoking gun, a fundamental difference in the behavior of matter and antimatter. The most famous of these is the search for an electric dipole moment in the neutron. Finding that a neutron has a slightly more positive side and a negative side would be a clear sign that the symmetry between matter and antimatter is broken in a way far stronger than anything we've seen before, potentially providing the missing piece of the puzzle. The resolution of the baryon asymmetry mystery is more than just an academic exercise. It is a quest to understand our own existence. That 1 in a billion imbalance was the ultimate cosmic contingency plan. Without it, there would be no atoms, no chemistry, no planets, and no physicists to wonder why. Every structure in the universe, from the largest galaxy cluster to the smallest cell in your body, is made from the leftover crumbs of a near-total annihilation that occurred at the dawn of time. We are literally made of stardust, but more fundamentally, we are made of something far rarer, the residual evidence of a broken symmetry, the saved relics of a universe that chose to favor something over nothing. But what if the answer to one of our greatest cosmic puzzles, the nature of dark matter, has been hiding not in a new particle, but in the most extreme gravitational objects we know? This brings us to a fascinating and speculative idea that the universe is teeming with ancient black holes forged in the fires of creation itself. The theory of primordial black holes suggests that in the extreme density of the early universe, mere moments after the Big Bang, random fluctuations could have collapsed directly into black holes. Unlike the stellar mass black holes we know, which form from the death of massive stars, these primordial ones could have been born with almost any mass, from smaller than a pebble to larger than a star. The most compelling aspect of this theory is that these ancient objects could, in fact, be the dark matter we've been searching for. If vast numbers of these primordial black holes were created and then scattered throughout the cosmos, their collective gravitational pull would be immense, yet they would emit no light, perfectly matching the description of the invisible matter that binds galaxies together. They would have been present from the very beginning, providing the gravitational seeds around which the first stars and galaxies could coalesce. This would elegantly solve the problem of how structure formed so quickly in the early universe. You wouldn't have to wait for dark matter particles to slowly clump together. The black holes would already be there, serving as instant gravitational anchors. Of course, a theory this bold requires evidence, and scientists have devised ingenious ways to hunt for these cosmic ghosts. One primary method is through gravitational microlensing. The idea is straightforward. If a massive, compact object like a primordial black hole passes directly between us and a distant star, its gravity will act like a tiny lens, bending the starlight and causing the star to temporarily brighten. Large-scale surveys, like those conducted with the optical gravitational lensing experiment or the Subaru telescope's hyper-subprime cam, continuously monitor millions of stars in nearby galaxies like the Andromeda, watching for these telltale flashes. The duration of the brightening event even tells us about the mass of the object causing it. A short flash might indicate an Earth mass black hole, while a longer one could point to something much heavier. Another potential signature is far more explosive and ties into Stephen Hawking's most famous prediction. Hawking realized that black holes are not completely black. Due to quantum effects at their event horizons, they should slowly evaporate, emitting a faint glow of radiation. For a massive black hole, this process is immeasurably slow. But for a very low-mass primordial black hole, the story is different. One with the mass of a mountain would be nearing the end of its multi-billion-year life, and its evaporation would culminate in a spectacular final fireworks display, a burst of high-energy gamma rays. Astronomers have searched the sky for these telltale explosions, and while a few candidates have emerged, none have provided definitive proof. The absence of such signals has actually helped scientists rule out entire ranges of masses for which primordial black holes could make up all of dark matter. This highlights the main challenge of the theory. It has to survive a gauntlet of astronomical constraints. If too many asteroid-mass primordial black holes existed, they would disrupt the tight orbits of stars in dense clusters. If too many moon-sized ones were zipping around, they would have left scars on the ancient surfaces of worlds like Pluto and Charon, which we don't see. The gravitational wave signals from merging black holes detected by LIGO have also opened a new window, providing a census of black hole masses in the universe. While some of these detections could potentially be primordial in origin, their numbers and masses aren't yet high enough to account for all the dark matter. The current data suggests that if primordial black holes are a component of dark matter, they likely exist within a narrow, allowed range of masses, perhaps between that of a large asteroid and the planet Neptune. Despite these constraints, the theory remains profoundly alluring because it requires no new physics beyond our well-tested theories of gravity and quantum mechanics. It posits that the dark matter mystery could be solved by objects we already know exist, just born through a different, more exotic channel. The ongoing search for them continues to push the boundaries of observation, forcing us to look at the universe in ever more creative ways. Whether they ultimately account for all dark matter or just a small fraction, the confirmed discovery of even a single primordial black hole would be a monumental find, a direct relic from the universe's first second of existence, offering an unparalleled glimpse into the conditions of creation itself. Now, from the behavior of particles to the vast architecture of the cosmos, we've explored forces that shape reality from the outside in. But what if one of the most profound forces is the one that shapes reality from the inside out, the force of consciousness itself? This brings us to one of the most speculative and controversial ideas at the frontier of science, the hypothesis that quantum mechanics might not just describe the universe, but might be the very engine of our awareness. This theory, most famously proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, suggests that the seat of consciousness may lie within the tiny, structural components of our brain cells called microtubules. To understand this, we first have to confront the so-called hard problem of consciousness. Neuroscience has made incredible strides in mapping which parts of the brain light up when we feel love, recognize a face, or solve a math problem. We can correlate brain activity with experience, but no one has yet explained how a 3-pound lump of fatty tissue, a collection of neurons firing electrochemical signals, gives rise to the rich, internal, subjective experience of being you. The feeling of the color red, the taste of chocolate, the ache of sadness. This gap between objective brain processes and subjective experience is the central mystery. Penrose and Hameroff propose that the answer might lie not in the chemistry of the brain, but in its physics, specifically its quantum physics. Their theory, called orchestrated objective reduction, or ORCH, posits that consciousness arises from quantum computations happening inside the microtubules within our neurons. Microtubules are intricate, lattice-like protein structures that act as the scaffolding of cells, helping them maintain their shape and transport materials. In neurons, they are incredibly abundant and organized. Penrose and Hameroff suggest that these microtubules are far more than simple scaffolding. They are ideal environments for hosting delicate quantum states. Within them, electrons could become quantumly entangled, existing in a superposition of states, a simultaneous yes/no, on/off condition. and these synchronized quantum vibrations could form the basis of a pre-conscious process. The theory then makes an even more radical leap, tying this process to the very fabric of space-time. Penrose had previously proposed a model for objective wave function collapse, suggesting that a quantum superposition becomes unstable and collapses into a single state not when it is observed, but when the difference in space-time curvature between the possibilities becomes too great. In this view, the collapse of the quantum wave function is a fundamental event in the universe. In the Orch or theory, each time such a collapse event occurs in the microtubules, it gives rise to a momentary blip of conscious experience. A stream of these events, orchestrated by the biological processes of the brain, would then create our continuous river of awareness. In essence, our consciousness would be a cascade of quantum gravitational events happening inside our own heads. Unsurprisingly, this hypothesis has faced fierce criticism from much of the scientific community. The primary objection is the issue of the environment. The brain is widely considered to be a warm, wet, and noisy place. Quantum states like superposition and entanglement are notoriously fragile. They are easily destroyed by interactions with their surrounding environment, a process called decoherence. This is why cutting-edge quantum computing experiments are conducted at temperatures near absolute zero in ultra-high vacuum chambers, isolated from all external vibration. Critics argue that the chaotic, warm environment of the brain would cause any delicate quantum state to decohere almost instantly, far too quickly to play any meaningful role in neural processes that occur on millisecond timescales. They maintain that classical physics is more than sufficient to explain the brain's information processing. Proponents of quantum consciousness, however, point to emerging evidence that biology might be far more quantum-friendly than we once thought. The field of quantum biology has found tantalizing examples of quantum effects at work in living systems. Photosynthesis, for instance, seems to use quantum coherence to achieve near-perfect efficiency in transferring energy in plants. Some birds are believed to use quantum entanglement in molecules in their eyes to navigate using the Earth's magnetic field. If nature has already evolved ways to harness quantum mechanics in green leaves and avian compasses, is it so outrageous to think it might have done so in the most complex object we know of the human brain? The idea remains on the fringe, a captivating what if that challenges our understanding of both the universe and ourselves, suggesting that the line between the objective external world and our subjective internal experience might be far blurrier than we ever imagined. But if the quantum nature of consciousness remains a fascinating speculation, another idea emerging from the physics of black holes presents a challenge to our most basic understanding of reality's very dimensions. This is the holographic principle, a theory that suggests everything we perceive in our three-dimensional universe, every galaxy, every person, every atom might actually be a projection of information encoded on a distant two-dimensional surface. It's the ultimate cosmic illusion, a reality where the world we experience is akin to an incredibly detailed and vivid hologram. The origins of this mind-bending idea are not found in science fiction, but in the hard thermodynamics of black holes. In the 1970s, physicist Jacob Bekenstein made a startling proposal. A black hole must have entropy. Entropy is a measure of disorder or information content, and Bekenstein realized that when matter falls into a black hole, its information isn't destroyed but is somehow encoded on the event horizon, the black hole's point of no return. He found that the entropy of a black hole, and therefore the amount of information it can contain, is proportional to the area of its event horizon, not its volume. This was a radical departure from everyday experience, where the information capacity of an object, like a hard drive or a book, depends on its three-dimensional volume. For a black hole, all the information describing everything that ever fell into it is somehow painted onto its two-dimensional surface. This discovery led to the famous formula known as the Bekenstein-Hawking entropy, a cornerstone of black hole physics. This revelation created a profound puzzle known as the black hole information paradox, famously highlighted by Stephen Hawking. Hawking showed that black holes slowly evaporate through the emission of radiation, and this Hawking radiation appears to be completely random, carrying no information about what fell in. If the black hole evaporates completely, the information it once contained would be lost forever, violating a fundamental tenet of quantum mechanics: that information cannot be destroyed. The holographic principle emerged as a potential solution. It boldly asserts that Bekenstein's discovery isn't just a quirky property of black holes, it's a fundamental principle of the universe. Perhaps all the information within any given volume of space is actually encoded on the boundary that surrounds it. The three-dimensional world is a projection of that data, much like a three-dimensional holographic image is generated from a two-dimensional film. To grasp this, imagine a classic hologram. On a flat piece of film, you'll see what looks like a meaningless pattern of swirls and lines. But when you shine a laser through it, a stunning three-dimensional image appears in midair. Every tiny piece of the two-dimensional film contains information about the entire three-dimensional image. The holographic principle applies this same concept to the entire cosmos. In one of its most concrete formulations, known as the AD/CFT correspondence, physicists demonstrated a full mathematical duality between a gravity-filled universe with 4 spacetime dimensions and a quantum field theory without gravity living on its three-dimensional boundary. This means that a theory describing the forces and particles in our world could be completely equivalent to a theory of quantum information dancing on a vast, distant surface we can never see. The implications of this for the nature of reality are nothing short of revolutionary. It suggests that the universe we perceive is not fundamentally made of particles and forces in a volume, but of bits of information on a surface. The apparent third dimension, along with gravity and the laws of physics as we know them, emerge from the complex processing of this cosmic data. Your experience of moving through a three-dimensional world, feeling the solidity of the ground beneath your feet, would be a magnificent illusion generated by this underlying informational code. This principle also provides an elegant resolution to the information paradox, as the information swallowed by a black hole is never truly inside it. It remains smeared across its event horizon, preserved even as the black hole evaporates. This idea forces us to reconsider the very nature of space and time. They may not be fundamental aspects of the cosmos, but rather emergent properties that arise from a deeper, more abstract layer of reality governed by information theory. The holographic principle blurs the line between the physical and the informational, suggesting that at its most basic level, the universe might be composed not of tiny strings or particles, but of bits, and that the laws of physics are essentially a cosmic programming language. While still a developing area of theoretical physics, the holographic principle stands as one of the most profound and radical ideas in modern science, hinting that the true nature of reality is far stranger and more wondrous than the world our senses present to us. If you thought the strangest states of matter were things like solids, liquids, or plasmas, prepare to have your understanding of reality fundamentally shifted. We now venture into the realm of a phase that shouldn't even be possible according to classical physics, a structure that moves perpetually without energy, breaking one of the most fundamental symmetries of the universe. These are time crystals, and they represent an entirely new non-equilibrium phase of matter that exists in a constant state of ordered motion, even in their ground state. The concept was first proposed by Nobel laureate Frank Wilczek in 2012, and it initially seemed to flirt with the impossible. A perpetual motion machine is forbidden by the laws of thermodynamics because it would require creating energy from nothing. But a time crystal is something altogether different and far more subtle. It doesn't create or output energy. Instead, it's a system that achieves a stable, repeating cycle of motion while in its lowest energy state. Imagine a perfectly frictionless ring. If you give it a spin, it will rotate forever, but that's just conservation of momentum. It's not a time crystal. Now imagine a ring that, even at absolute zero and completely isolated from the universe, spontaneously begins to pulsate, rotating back and forth in a fixed, unending rhythm without ever slowing down. That's the essence of a time crystal. It's not a crystal in the traditional sense of a spatially repeating atomic lattice like diamond or quartz. Instead, its atoms exhibit a pattern that repeats not in space but in time. This behavior directly challenges our notion of temporal symmetry. Most physical laws are symmetric in time, meaning they work the same whether time is moving forward or backward. The force of gravity, for instance, doesn't care about the arrow of time. A time crystal, however, spontaneously breaks this time translation symmetry. In its ground state, it chooses a specific rhythm, a specific ticking clock, out of all possible symmetric options. It's as if the system picks a preferred beat for the universe and stubbornly sticks to it. Creating such a system in the lab was a monumental task, as it required isolating a quantum system and putting it into its ground state while finding a way to initiate this perpetual ticking. The first successful demonstrations came in 2017, with two independent teams using very different approaches. One team used a chain of ytterbium atoms, while another used diamonds with dense nitrogen vacancies. In each case, the researchers kicked the system with a laser pulse, and instead of the response dying down as expected, the system locked into a stable, persistent rhythm that continued long after the initial push. Crucially, this rhythm occurred at a fraction of the frequency of the laser pulse, proving it was an emergent property of the system itself, not a simple echo of the external force. The potential applications for this discovery are as profound as they are futuristic. The most immediate impact could be in the field of quantum computing. One of the biggest hurdles for quantum computers is decoherence, the tendency for qubits to lose their fragile quantum state due to tiny interactions with their environment. A time crystal, with its inherent stability and resistance to external disruption, could potentially serve as a perfect, self-correcting quantum memory device. Its robust periodic structure could provide a stable reference frame for other qubits, helping to maintain their coherence for vastly longer periods and bringing us closer to practical, large-scale quantum computers. Beyond computing, time crystals could lead to impossibly precise sensors. A clock built from a time crystal's unwavering rhythm could measure magnetic fields or temperature gradients with an accuracy far beyond anything we have today, allowing us to detect the subtlest whispers of the quantum world. But perhaps the most mind-bending implication is for our understanding of time itself. Time crystals demonstrate that the arrow of time, the irreversible flow from past to future that we all experience, might not be a universal constant but an emergent property that arises from specific systems breaking temporal symmetry. They are a tangible, physical manifestation of a system that has its own internal clock, its own fundamental rhythm woven into the fabric of reality. Studying them could provide unprecedented insights into the nature of time, entropy, and the ultimate laws that govern our universe, showing us that even in a state of perfect rest, the cosmos is still and always humming with motion. While the gravitational influence of dark matter weaves the cosmic web, giving the universe its large-scale structure, another invisible force silently threads through this entire architecture, shaping the lives of galaxies and the particles that race between them. This is the cosmic magnetic field, a pervasive and dynamic presence that stretches from the hearts of planets to the unimaginable voids between galaxy clusters, forming a vast, interconnected web of its own. We often think of magnetism as the simple force that holds a note to a refrigerator or guides a compass needle, but on a cosmic scale, it is a fundamental sculptor of reality. influencing everything from the birth of stars to the journey of the most energetic particles in the universe. These magnetic fields originate from the movement of charged particles, a principle known as the dynamo effect. Within a planet like Earth, the churning of molten iron in its outer core generates a powerful planetary magnetic field that extends far out into space, creating a protective bubble called the magnetosphere. This shield deflects the relentless stream of charged particles from the sun, the solar wind, protecting our atmosphere and making life possible. The same process occurs on a grander scale within stars and even in the turbulent gas between them. But the true mystery lies in the origin of the first, seed magnetic fields in the early universe. How did a universe that began with no apparent large-scale magnetic structure become so thoroughly magnetized? The leading theories suggest that tiny, quantum-scale fluctuations in the primordial plasma were amplified by the motions of that plasma in the infant cosmos. These weak fields were then stretched, twisted, and supercharged by the colossal forces of gravitational collapse and rotation as the first galaxies formed, eventually growing into the powerful fields we detect today. The influence of these fields is most dramatically visible in the process of star formation. A vast cloud of gas and dust, a stellar nursery, begins to collapse under its own gravity. As it contracts, it spins faster, much like a figure skater pulling in their arms. Without a magnetic field, this process would be inefficient. The cloud would fragment and form many small stars. But magnetic fields act as a cosmic brake, transferring angular momentum away from the central core and allowing the gas to flow inward more smoothly. They also provide support against gravity, slowing the collapse and ultimately helping to determine the final mass of the newborn star. In some stunning astronomical images, we can actually see the evidence of this magnetic sculpting. Observations of clouds like the pillars of creation reveal that the dust grains, which are slightly magnetic, align themselves with the local field lines. When we measure the polarized light from these grains, we can map the magnetic field structure, which often appears as elegant, sweeping curves guiding the flow of matter, as if the universe itself is drawing a blueprint for a new solar system. Beyond individual stars, magnetic fields are crucial drivers of galactic evolution. They are tightly woven into the spiral arms of galaxies like our Milky Way, and they play a key role in one of a galaxy's most important life cycles, the recycling of matter. When massive stars die in supernova explosions, they eject their enriched contents back into space. The expanding shock waves from these explosions travel through the interstellar medium, and the galactic magnetic field helps to channel and contain this material, preventing it from simply dissipating into the void. This process helps to create vast supershells of gas and triggers new waves of star formation. Furthermore, magnetic fields are essential for launching and confining the colossal jets of material that erupt from the active supermassive black holes at the centers of many galaxies. These jets can extend for hundreds of thousands of light years, and they are only able to maintain their incredibly narrow, focused structure because they are tightly collimated by powerful magnetic fields, which act like the barrel of a cosmic rifle. Perhaps the most dramatic role of the cosmic magnetic web is its effect on cosmic rays. These are not rays of light, but rather high-energy atomic nuclei, mostly protons, accelerated to nearly the speed of light by supernova shocks and other violent astrophysical events. Because they are charged particles, their paths are completely dominated by magnetic fields. As a cosmic ray travels through space, the galactic magnetic field bends its trajectory, turning what would be a straight line into a chaotic, spiraling path. This has two profound consequences. First, it makes it utterly impossible to trace a cosmic ray directly back to its source. By the time it reaches us, it has been scrambled by millions of years of wandering through the magnetic maze of the galaxy. Second, this magnetic confinement means that cosmic rays are effectively trapped within the Milky Way for millions of years. bouncing back and forth across the galactic disk and contributing significantly to the energy balance and pressure of the interstellar medium. They are the ultimate cosmic pinballs, and the magnetic field is the intricate playfield they bounce through. Mapping this invisible force is one of the great challenges of modern astronomy. We cannot see magnetic fields directly, but we can detect their influence through the light that passes through them. As light travels through space filled with magnetically aligned dust grains, it becomes polarized. Sophisticated instruments on telescopes like the Stratospheric Observatory for Infrared Astronomy and the upcoming Square Kilometre Array are designed to measure this faint polarization across the sky. These observations are allowing us to create the first detailed maps of the magnetic field within our own galaxy, revealing a stunningly complex tapestry of lines that weave through the spiral arms. On even larger scales, astronomers use the faint polarization of the cosmic microwave background and the way magnetic fields affect the radio waves from distant galaxies to probe the magnetic web that connects entire clusters of galaxies. This vast, unseen architecture is a fundamental component of the cosmos, a force that guides, contains, and energizes the universe on every scale, proving that even in the apparent emptiness of space, there is no such thing as a true void. But as we grapple with the bizarre implications of quantum mechanics, from entanglement to the uncertainty of the vacuum, a profound question remains: why do we, as observers, perceive a single, stable, and objective reality? If the quantum world is fundamentally a blur of probabilities and superpositions, why doesn't a chair spontaneously vanish or exist in two places at once from our perspective? The answer may lie not in the quantum realm itself, but in how it interacts with everything else, a process that gives rise to the world we know through a principle known as quantum Darwinism. This theory suggests that the classical reality we experience isn't the default state of the universe, but rather an emergent property, a consensus view that has been sculpted by a constant process of environmental interaction and selection. To understand this, we must first confront the core weirdness of quantum mechanics. In its pristine, isolated state, a quantum system exists in a superposition of all possible states. An electron isn't simply spinning up or down, it is in a fuzzy combination of both, a potentiality waiting to be realized. The traditional Copenhagen interpretation of quantum mechanics posits that this wave function collapses into a single, definite state only when it is observed or measured. But this raises an awkward question. What counts as an observer? Is it a conscious human, a cat in a box, a photon hitting a detector? This is the infamous measurement problem, and it has plagued physicists for a century. Quantum Darwinism offers a way out by eliminating the need for a special, privileged observer. Instead, it proposes that the act of observation is happening constantly, everywhere, all the time, through a process called decoherence. Decoherence is the mechanism by which a quantum system loses its coherence, its ability to exhibit quantum weirdness like superposition and interference by interacting with its environment. Think of the environment not as empty space, but as a bustling sea of particles, photons of light, air molecules, the cosmic microwave background radiation, even the subtle gravitational pull of distant stars. A fragile quantum system cannot remain isolated from this chaos for long. The moment it interacts with even a single photon from the environment, that photon becomes correlated with the system. It effectively gains information about it. This interaction is like making a copy of the quantum system's state and broadcasting it out into the world. As more and more environmental particles interact with the system, countless copies of its state are made and scattered. This proliferation of information is what destroys the delicate quantum superposition. The system is no longer in a fuzzy mix of states because the environment now knows which state it is in. It's not that the wave function collapses, it's that the quantum information becomes so widely dispersed and copied into the environment that the system effectively behaves classically. This is where the Darwinian selection comes in. Not all information about a quantum system is copied equally into the environment. Some properties are robust and leave a strong, durable imprint. These are the pointer states, and they are naturally selected for because they can withstand the constant bombardment of environmental interaction without being drastically altered. A particle's position, for example, is a classic pointer state. When a dust mote is sitting on a table, countless photons from the room's light bounce off it, each one carrying away information about where it is. This massively redundant copying of its position into the environment means that any observer, whether a human, a camera, or another particle, will consistently find the dust mote in that same location. They all agree on the same objective reality because they are all accessing the same widely broadcast information. Other, more fragile quantum properties, like a specific phase relationship between states, are quickly erased by decoherence because they cannot survive the environmental interaction. They don't get copied, so they simply don't contribute to our perceived reality. In this view, the world we see is not the entire quantum menu. It is merely the daily special, the subset of quantum possibilities that are stable enough to be repeatedly measured and agreed upon by countless independent observers. Our classical reality emerges from a form of natural selection where the environment acts as a selective amplifier for certain types of information. This is quantum Darwinism, the survival of the fittest information. The redundancy of this information is key. You don't need to perform a complex, destructive measurement on a system itself to know its position. You can simply intercept a few of the trillions of photons that have already scattered off it and encoded that data. This is why we all agree on the location of the moon, the solidity of the ground, and the existence of the sun. Their states have been so redundantly imprinted onto the environment that they become objective facts, independent of any single observer. This framework elegantly bridges the gap between the quantum and classical worlds without invoking any mysterious consciousness-driven collapse. It suggests that objectivity is actually a form of consensus reached through the relentless copying of information. The universe, through decoherence, is constantly performing measurements on itself, and we, as embedded observers, are simply tapping into that pre-existing, widely distributed data stream. The strange quantum underpinnings are still there, but they are hidden from our view, masked by the overwhelming consensus of the environment. What we perceive as the definite, concrete world is therefore a robust illusion, an emergent layer of reality that has been distilled from the quantum possibilities by the relentless and selective pressure of simply existing in a universe that is always and everywhere watching. Yet if quantum Darwinism explains the emergence of our familiar three-dimensional reality, could it be that this reality is merely the visible portion of a far more complex and hidden cosmic architecture? This brings us to a concept that stretches the imagination to its absolute limit, the possibility that our universe is not three-dimensional at all, but instead possesses extra spatial dimensions curled up into sizes so infinitesimal that they remain completely invisible to our senses. The idea that space might have more than the three dimensions we experience, length, width, and height, is not just science fiction. It is a serious proposal within modern theoretical physics, one that could elegantly solve some of the universe's most puzzling mysteries. The most immediate puzzle that extra dimensions might explain is the shocking weakness of gravity. Think about the fundamental forces for a moment. A small kitchen magnet can overcome the gravitational pull of the entire Earth to lift a paperclip. Why is gravity so unimaginably feeble compared to the electromagnetic force or even the nuclear forces? If all forces originated from a similar foundation, we might expect them to be of comparable strength. One compelling explanation is that gravity is not weak. It only appears weak because it is not entirely confined to our three-dimensional brain of reality. In this scenario, known as the brain-world model, the three dimensions we know could be a membrane floating within a higher dimensional space. while the other forces, like electromagnetism, are stuck to our brain. Gravity, which is the curvature of spacetime itself, can leak out into these extra dimensions. Its strength would be diluted as it spreads out, explaining why it feels so weak from our perspective. It's not that gravity is inherently weak. We are simply experiencing only a tiny fraction of its full strength, with the rest leaking away into dimensions we cannot perceive. But how could additional dimensions exist without us noticing them? The answer lies in a process called compactification. Imagine a long, thin garden hose stretching far into the distance. From a great distance, it looks like a simple one-dimensional line. But if you were an ant crawling on that hose, you would discover a second dimension, the circular path around its tube. The dimension is still there, but it is curled up into a tiny, compact size. Physicists propose that the extra dimensions of space could be similarly compactified, curled up into intricate, tiny shapes at every single point in our familiar three-dimensional space. These shapes, known as Calabi-Yau manifolds, are complex mathematical forms with 6 or 7 dimensions, all folded up at the Planck scale, a distance so small that a direct observation is currently impossible. At every location in the room you're in, there isn't just a point. There is an entire, fantastically complex 6-dimensional geometric shape, but it is so small that it is completely invisible to us and our instruments. Our particle accelerators simply don't have enough energy to probe such tiny scales and excite particles into these hidden dimensions. The most famous framework that incorporates these ideas is string theory. For the complex mathematics of string theory to work, to be free of absurdities like negative probabilities, it requires a specific number of spacetime dimensions, 10. This means that in addition to the one dimension of time and the 3 expansive dimensions of space we move through, there must be 6 additional spatial dimensions that are compactified. In string theory, the fundamental particles aren't point-like dots. They are tiny, vibrating strings. The different ways these strings vibrate in the multi-dimensional geometry determine the properties of the particles we observe, such as their mass and charge. An electron is simply a string vibrating one way, while a quark is a string vibrating another. Crucially, one particular vibration pattern is believed to correspond to the graviton, the hypothetical particle that mediates gravity. This is how string theory naturally incorporates gravity into the quantum world, offering a potential path to the long-sought theory of everything. The specific properties of the compactified Calabi-Yau shapes would determine the constants of nature, like the charge of an electron or the strength of gravity. In a sense, the entire universe we see is dictated by the hidden geometry of these invisible dimensions. Another fascinating model that utilizes extra dimensions is the Randall-Sundrum model, which proposes a radically different setup. Instead of being tiny and curled up, the extra dimension in this theory could be large or even infinite. However, the force of gravity would be localized on a different brane than our own, separated by this warped extra dimension. This warping creates an exponential dimming of gravity's influence, explaining its apparent weakness without requiring extremely small dimensions. This model also provides a potential solution to the hierarchy problem, the enormous discrepancy between the strength of gravity and the other forces, by using the geometry of the higher dimensional space itself to explain why the fundamental scale of gravity, the Planck scale, is so much different from the scale of the electroweak force. The search for experimental evidence of these extra dimensions is a driving force behind modern particle physics. While we cannot see them directly, we might detect their influence indirectly. The Large Hadron Collider is not just a machine for finding particles, it is also a microscope for probing the fabric of space-time at unprecedented resolutions. One tantalizing signature of extra dimensions would be the sudden disappearance of energy. If 2 particles collide and some of the energy of the collision vanishes, it could be a sign that the energy was carried away by a graviton escaping into a higher dimension. Another potential signature would be the discovery of microscopic black holes. In a higher dimensional universe, the strength of gravity increases dramatically at very short distances because it is no longer diluted. This could make it possible to form tiny, quantum-sized black holes at energy scales achievable by the LHC. These black holes would instantly evaporate via Hawking radiation, leaving behind a very specific shower of particles in the detectors. While no definitive evidence has been found yet, the hunt continues, pushing the boundaries of both energy and imagination. The existence of extra dimensions would forever alter our perception of reality, revealing that the cosmos is infinitely more vast and complex than it appears, with hidden depths folded into the very fabric of space itself. This idea that the very laws of physics seem suspiciously hospitable to our existence is known as the anthropic principle, and it stands as one of the most profound and debated observations in all of science. It's the recognition that the universe is not just capable of producing life, it appears to have been calibrated for it from the very beginning. Consider the fundamental constants that govern reality, the numerical values that are simply plugged into the equations of physics. These aren't derived from any deeper theory. They are, as far as we know, brute facts of existence. And yet, if any one of them were even slightly different, the universe as we know it would be impossible. The strength of the strong nuclear force is a perfect example. This is the glue that holds atomic nuclei together. If this force were just a few % stronger, two protons would be able to bind together directly. This would cause all the hydrogen in the early universe to fuse into helium and then into heavier elements almost instantly. Stars like our Sun, which slowly burn hydrogen over billions of years, would never form. There would be no long-lived stars to warm planets and no stable stellar environments for life to evolve. Conversely, if the strong force were slightly weaker, protons and neutrons wouldn't stick together at all. Deuterium, a crucial stepping stone in the chain of nuclear fusion inside stars, would be unstable. Without deuterium, the fusion process that powers stars would never ignite. The universe would be a cold, dark soup of hydrogen, utterly barren and inert. The force is poised on a razor's edge, allowing for a complex and life-giving cosmos. This fine-tuning extends to the very expansion rate of the universe, set by the initial conditions of the Big Bang. The balance here is so precise it defies belief. If the universe had expanded just a tiny bit faster after the Big Bang, matter would have spread out too rapidly for gravity to pull it together into galaxies and stars. The cosmos would be an ever-diluting, lonely void. If it had expanded just a tiny bit slower, gravity would have quickly reversed the expansion, causing the entire universe to collapse back in a big crunch before any stars could even form. Our universe's expansion rate hit a perfect golden mean, allowing for structure to form without immediately collapsing or flying apart. Even the amount of entropy, the initial smoothness of the universe, was perfectly set to allow for the gradual formation of galaxies rather than a rapid descent into chaos or a static, featureless expanse. Faced with this staggering array of cosmic coincidences, scientists and philosophers have proposed several explanations, each more mind-bending than the last. The first is simply to accept it as a staggering piece of luck, a happy accident with no deeper meaning. But for many, the odds are so astronomically against such a perfect combination of constants that this answer feels profoundly unsatisfying, almost like a refusal to engage with the mystery. A second explanation ventures into the realm of theology or intelligent design, suggesting a cosmic architect set the dials to the correct values. While this provides an answer, it lies outside the realm of scientific inquiry, effectively ending the conversation rather than deepening it. This is where the third, and perhaps most scientifically compelling, explanation comes in: the multiverse. If our universe is just one of a vast, perhaps infinite, number of universes, each with its own random set of physical constants and laws, then the mystery of fine-tuning vanishes. In such a multiverse, most universes would be stillborn or sterile. their physical laws incapable of generating atoms, chemistry, or complexity. But by the sheer law of large numbers, a few universes would, by pure chance, have the perfect combination of constants for life to arise. And of course, we find ourselves in one of those rare, habitable universes because we couldn't possibly exist anywhere else. Our presence here is a form of observational selection bias. We are the living proof that our universe's lottery ticket was a winner. The multiverse idea doesn't make fine-tuning less amazing, but it reframes it from a mysterious intention to a statistical inevitability within a grander cosmic landscape. The challenge, of course, is that the multiverse is currently untestable. These other universes, by definition, would exist in domains completely separate from our own observable cosmos, with no possibility of communication or observation. For some, this makes the multiverse an unscientific concept, little more than a metaphysical speculation. For others, it's the most natural extension of our current best theories, like cosmic inflation, which seems to naturally produce a bubble universe multiverse as part of its mechanics. Whether the anthropic principle points to a staggering accident, a divine hand, or a multiverse, it forces us to confront the deepest questions about reality, our place within it, and whether the universe is, in some profound sense, meant to be known. Yet for all its mind-bending implications, the holographic principle and its vision of a projected reality might find their ultimate validation in the chaotic, churning nature of the void itself when we look at the universe on its very smallest possible scale. This brings us to a concept that challenges the very idea of smooth, continuous space, suggesting that the fabric of reality is fundamentally rough and turbulent. This is the theory of quantum foam, the hypothetical texture of spacetime at the Planck scale, where the notion of a calm, geometric continuum shatters into a seething, probabilistic frenzy. To grasp this idea, we need to journey down to the absolute limits of measurement, to a distance known as the Planck length. This is about 10 to the minus 35 meters, a scale so vanishingly small that it is to a single proton what that proton is to a large city. At this incredible scale, the smooth, predictable spacetime described by Einstein's general relativity is expected to break down completely. The reason lies in the fundamental trade-off at the heart of quantum mechanics, the Heisenberg uncertainty principle. This principle doesn't just apply to a particle's position and momentum, it also applies to energy and time. It implies that on extremely short timescales, there can be massive uncertainties in energy. This allows for the spontaneous creation of pairs of virtual particles, as we see in the quantum vacuum, but it also has a profound implication for the geometry of spacetime itself. The energy required to probe such tiny distances is so immense that it would inevitably warp and distort the very region of spacetime you are trying to measure. Imagine trying to map the surface of a pond by hitting it with a sledgehammer. The act of measurement itself creates violent waves that obscure the details you're looking for. In the same way, at the Planck scale, the energy fluctuations are so violent that they prevent spacetime from ever settling into a calm, smooth state. Instead, it is theorized to become a chaotic, turbulent foam. In this quantum foam, the concepts of before and after and here and there lose all meaning. The topology of space itself is no longer fixed but fluctuates wildly. Microscopic wormholes might blink into existence, connecting two distant points before vanishing again. Tiny virtual black holes could form and evaporate in a fraction of a Planck time. The smooth, four-dimensional continuum we experience is just a large-scale average, an illusion that emerges from this unimaginably complex and frothy underlying activity, much like the smooth surface of water emerges from the chaotic motion of countless molecules. This frothy nature of spacetime isn't just a theoretical curiosity. It could have observable consequences for the most energetic travelers in the cosmos, photons. Light from distant astrophysical phenomena like gamma-ray bursts or active galactic nuclei can travel for billions of years to reach us. According to some models of quantum foam, these ultra-high-energy photons should interact with the foamy texture of spacetime on their long journey. This interaction wouldn't slow them down, but it could subtly randomize their path, causing a slight blurring or a minute delay between photons of different energies. It would be an effect similar to light being scattered by a fog, but a fog made of spacetime itself. Detecting this effect is incredibly difficult, as the expected time difference is on the order of a few milliseconds across the entire history of the universe. Yet astronomers continue to analyze the light from the most distant and violent events, searching for this telltale signature of a foamy reality. Finding it would be direct evidence that Einstein's smooth spacetime is indeed an approximation, a calm ocean surface hiding a turbulent and discontinuous depth. Forcing our perspective beyond the cosmic speed limit brings us to one of the most speculative and fascinating ideas in theoretical physics, the concept of tachyons. These are not particles from science fiction, but rather a serious, albeit highly conjectural, consequence of the mathematics of Einstein's special relativity. The equations don't just describe the world of particles with mass that travel below the speed of light, or massless particles like photons that travel exactly at it. They also permit solutions for particles that always travel faster than light. These hypothetical entities are tachyons, a name derived from the Greek word tachys, meaning swift. The most startling property of a tachyon is its relationship with mass. In our familiar world, a particle at rest has what we call its rest mass. As it accelerates, its relativistic mass increases, and it requires more and more energy to approach the speed of light. For a tachyon, this relationship is inverted. A tachyon's squared mass is a negative number, an imaginary value. This means it would require energy to slow it down to the speed of light. Its natural state is to zip along at superluminal velocities, and trying to break it to light speed would take an infinite amount of energy. If you could somehow give it even more energy, it would actually go faster. Their very existence would imply a universe where the speed of light is not an upper barrier to be approached, but a lower barrier to be exceeded. The immediate and most glaring problem with anything moving faster than light is the potential for violating causality, the principle that cause must always precede effect. This is the backbone of our logical understanding of the universe. If you could send a signal faster than light according to special relativity, there would be some reference frames from which that signal would appear to arrive before it was sent. This could create insurmountable paradoxes like the famous grandfather paradox, where an effect could prevent its own cause from ever happening. It's precisely this potential for logical chaos that leads most physicists to believe superluminal communication is impossible. However, some theoretical frameworks suggest a way that tachyons might exist without ripping apart the fabric of cause and effect. This hinges on a critical distinction between a tachyon as a localized particle that could carry a specific message and a tachyon as a feature of a field. In quantum field theory, the universe is not made of discrete balls, but of underlying fields: the electron field, the quark field, the Higgs field. Particles are simply localized excitations or quanta of these fields. The stability of these fields is paramount. If the Higgs field, for instance, were perched at a local maximum of its energy potential rather than sitting comfortably in its minimum, it would be in a false vacuum state, unstable and ready to decay. This is where the tachyon concept finds a more respectable home. In this context, tachyonic doesn't describe a particle zipping through space, but rather describes the unstable state of a field itself. A tachyonic instability occurs when the mass term in a field's equation becomes negative, signifying that the current configuration of the field is unstable. The field wants to condense or roll down to a new, stable state where its quanta have a positive, real mass. This process, called tachyon condensation, is not about things moving faster than light. It's about a phase transition in the underlying field. This is a well-understood mechanism in string theory and other advanced frameworks, where the presence of a tachyonic mode in the spectrum of a string signals that the configuration is unstable and must decay into a more stable state, often one with a different topology altogether. In this view, the tachyon isn't a messenger of paradox but a herald of change, a mathematical flag that the universe is settling into a more stable, lower energy configuration. But if the quantum foam represents the chaotic, chiseled texture of spacetime at the smallest scales, the very ability of light to travel across that foam is governed by two of the most perfectly tuned numbers in all of physics. These are the vacuum permittivity and permeability constants, and while their names might sound intimidating, they represent something truly profound. The fixed, immutable properties of nothingness itself that allow everything from a radio signal to the light from a distant star to reach our eyes. Think of the vacuum of space not as a true void, but as a kind of medium with inherent electrical and magnetic properties. The vacuum permittivity, often denoted by the Greek letter epsilon-0, essentially measures how much resistance empty space puts up against the formation of an electric field. It's a measure of how easily the vacuum can be polarized by electric charges. Conversely, the vacuum permeability, denoted by mu0, quantifies how much resistance the vacuum offers to the formation of a magnetic field. Together, these two constants act like the fundamental elasticity and stiffness of spacetime when it comes to electromagnetic phenomena. They are the rules of the game for how electric and magnetic fields interact, propagate, and influence each other in the complete absence of any matter. Their individual values might seem arbitrary, but their relationship is where the magic happens. When you multiply epsilon-0 and mu0 together and then take the square root of that product, you don't get another abstract number. You get one of the most famous constants in the universe, 1 over the speed of light. This simple, elegant equation, c equals 1 over the square root of epsilon-0 times mu0, is breathtaking. It tells us that the speed of light isn't some arbitrary speed limit tacked onto the universe as an afterthought. It is a direct, inevitable consequence of the electromagnetic properties of the vacuum itself. Light, as an electromagnetic wave, is simply traveling at the only speed it possibly can, given how stiff or elastic spacetime is to electric and magnetic fields. The cosmic speed limit is written into the very fabric of empty space. This deep connection means that if either of these constants were even slightly different, the consequences would be catastrophic. A change in epsilon-0 would alter the strength of the electric force between charged particles. This would change the energy levels of electrons orbiting atomic nuclei, completely reshaping the entire periodic table of elements. The chemical properties of everything would change, and the complex molecules necessary for life might never form. A change in mu0 would similarly distort magnetic forces, disrupting everything from the stability of atoms to the magnetic fields that channel the solar wind. But most dramatically, a change in either would directly alter the speed of light. Since the fine structure constant, which governs the strength of electromagnetic interactions, is itself a combination of the speed of light, Planck's constant, and the charge of the electron, tweaking the speed of light would throw the entire delicate balance of physics into chaos. The universe would either be a turbulent plasma where atoms couldn't hold together, or a stagnant, inert void where forces were too weak to create any structure at all. The fact that these constants have the exact values they do, values that allow for a stable, complex, and life-permitting universe, is yet another staggering example of cosmic fine-tuning. They are not derived from any deeper theory. They are fundamental inputs, and their precise values are measured with incredible accuracy in laboratories around the world. Their stability is the bedrock upon which all of modern technology is built, allowing engineers to design every electrical circuit, every antenna, and every fiber optic cable with the absolute certainty that the rules of electromagnetism will not change. They are silent, unseen pillars upholding our reality, defining the boundaries of possibility for light and energy, and ensuring that the emptiness between the stars is not a true nothing, but a structured stage perfectly set for the drama of the cosmos to unfold. But if the very act of observation can fundamentally alter a quantum system, what happens when you watch it not just once but continuously? This brings us to one of the most counterintuitive and powerful effects in all of quantum mechanics, a phenomenon where simply staring at something with enough intensity can literally freeze it in place. This is the quantum Zeno effect, named after the ancient Greek philosopher Zeno of Elea and his famous paradoxes about motion being an illusion. Zeno argued that before an arrow can reach its target, it must first travel half the distance, then half of the remaining distance, and so on, leading to an infinite number of steps and the conclusion that motion is impossible. While flawed in the classical world, this idea finds a bizarre and literal truth in the quantum realm. At its heart, the quantum Zeno effect is a direct consequence of the wave function collapse we associate with measurement. Recall that an unobserved quantum system evolves smoothly over time, its probability wave spreading out, but the moment you measure it, you force it to collapse into a definite state. Now imagine you have a quantum system that is unstable, an atom in an excited state that is poised to decay and emit a photon, or a particle that is about to tunnel through a barrier. Left to its own devices, its probability of decaying or tunneling increases steadily over time. However, if you repeatedly measure it, asking it over and over again, are you still in your initial state? You continually reset its evolutionary clock. Each measurement collapses the wave function back to the starting point, preventing it from evolving away into other possibilities. With measurements coming in rapid succession, the system simply doesn't have enough time between observations to develop a significant probability of having changed. You have effectively paralyzed it with your gaze. This isn't just a theoretical curiosity, it has been demonstrated in laboratories around the world. One of the most famous early experiments involved thousands of beryllium ions trapped in a magnetic field and laser cooled to near absolute zero. These ions were prepared in a coherent superposition of two energy states, a delicate, evolving quantum state. Researchers then hit them with a series of rapid laser pulses, each pulse acting as a measurement. They found that by increasing the frequency of these pulses, they could dramatically slow down the evolution of the quantum state. The more frequently they looked at the system, the more effectively they could freeze it in its initial configuration, providing stunning experimental confirmation that observation truly does alter reality in a measurable, controllable way. The practical implications of this effect are profound, especially for the burgeoning field of quantum computing. The greatest enemy of a quantum computer is decoherence, the loss of the fragile quantum state of its qubits due to interactions with the external environment. The quantum Zeno effect offers a potential strategy to fight this decay. By constantly and gently monitoring the state of the qubits, not to read their data but simply to check if they are still in their correct state, it might be possible to actively suppress the errors that lead to decoherence. It's a form of quantum error correction that uses the act of observation itself as a protective shield, effectively holding the qubit in the desired state through a constant, low-intensity vigil. This turns the problem of measurement on its head, using what was once considered a destructive process as a tool for preservation. Beyond the lab, the quantum Zeno effect forces us to confront the deepest questions about the role of consciousness and reality. If a continuous observation can freeze a system, does that imply a continuous observer? It adds a fascinating layer to the old philosophical thought experiment. If a tree falls in a forest and no one is around to hear it, does it make a sound? The quantum version might be, if a radioactive atom decays and no one measures it, did it truly decay at a specific moment? The Zeno effect suggests that without some form of interaction or measurement to define its timeline, the very concept of a specific moment of change might be a Chinese letter. It paints a picture of a universe where things don't just happen, they are prompted to happen through interaction, and where a persistent enough attention can literally shape the unfolding of events, locking possibility into a single, stubborn reality. Yet after that primordial burst of expansion smoothed the infant universe, it left behind a permanent, cooling whisper, a cosmic fingerprint that now permeates all of space. This is the cosmic microwave background radiation, and it is the single most important artifact we have from the universe's infancy. Imagine the universe about 380,000 years after the Big Bang. Before this moment, it was an opaque, searing hot plasma, so dense that light particles, photons, were constantly scattered and trapped by a thick fog of free electrons and protons. Light could not travel in a straight line. It was a chaotic, glowing soup, but as the universe expanded and cooled, it underwent a monumental phase change. The electrons and protons finally had enough energy to combine and form the first stable hydrogen atoms in an event called recombination. This was the moment the universe became transparent. With the charged particles now bound into neutral atoms, the fog lifted. The photons, which had been trapped for eons, were suddenly set free. They began streaming across the universe in every direction, and they have been traveling ever since. We detect that ancient light today as the cosmic microwave background. It is the oldest light we can possibly see, a snapshot of the universe when it was a mere infant. But this isn't just a uniform wall of noise. It is imprinted with incredibly subtle patterns, tiny variations in temperature that look like a static television screen. These tiny fluctuations, mere millionths of a degree, are the seeds of all cosmic structure. They represent the slight over-densities and under-densities in that primordial plasma. The gravitational wells that would, over billions of years, pull in matter to form the first galaxies, stars, and eventually us. Mapping these imprints with exquisite precision has been the life's work of satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and most recently, the Planck spacecraft. These observatories have spent years staring into the depths of space, meticulously measuring the temperature of this microwave glow across the entire sky. The resulting maps are like a cosmic treasure trove of information. By analyzing the statistical properties of these hot and cold spots, their sizes, their distribution, and how they correlate with each other, cosmologists can read the universe's vital signs with astounding accuracy. The patterns in the background radiation tell us the universe's exact age, 13.8 billion years. They reveal its overall geometry with incredible precision, confirming that on the largest scales, the cosmos is flat to within a margin of error of just 0.4%. They also provide a complete inventory of the universe's contents, quantifying the exact amounts of ordinary matter, and dark energy. Perhaps most profoundly, these imprints are a direct window into the universe's very first moments. The specific pattern of fluctuations we see is a perfect match for the predictions of cosmic inflation, that rapid exponential expansion we discussed earlier. The theory predicted that quantum jitters from the inflationary epoch would have been stretched across the cosmos, creating a very specific signature in the microwave background. The data from Planck and other missions matches this prediction exactly. We are essentially seeing the magnified quantum fluctuations from a time when the entire observable universe was smaller than a single atom. The cosmic microwave background is therefore more than just an afterglow. It is a literal message from the dawn of time, a fossilized echo of creation that confirms our deepest theories about how everything began. It is the closest we will ever come to having a baby picture of the entire cosmos, and it tells a story written in the faintest variations of heat, a narrative of origin encoded in the cold of space. Yet for all the cosmic forces that build and shape reality, it was Stephen Hawking who unveiled one that subtly unravels it, a discovery so profound it created a paradox at the very heart of physics, forcing us to question whether the universe fundamentally forgets. This is the mystery of Hawking radiation and the terrifying information paradox it spawns. For centuries, black holes were the ultimate cosmic vacuums, regions of spacetime where gravity was so intense that nothing, not even light, could escape their clutches. They were the end of the line, the universe's one-way doors. Anything that crossed the event horizon was lost forever, swallowed into a singularity where the known laws of physics ceased to exist. This simple picture, however, contained a hidden time bomb for physics, one that Hawking would accidentally detonate by applying quantum mechanics to the edge of a black hole. Hawking's brilliant insight was to ask what happens to the quantum vacuum near the event horizon. Remember that empty space is not truly empty. It is a seething foam of virtual particle pairs constantly blinking in and out of existence. Normally, these pairs annihilate each other so quickly that they don't violate energy conservation. But Hawking realized that if this quantum fluctuation occurs right at the edge of a black hole's event horizon, the immense gravitational pull could tear the pair apart before they have a chance to recombine. One particle falls into the black hole while the other, its partner, escapes into space. To an outside observer, this escaping particle looks exactly like radiation emanating from the black hole itself. The energy for this radiation has to come from somewhere, and it comes from the black hole's own mass. The particle that fell in has negative energy, which effectively reduces the mass of the black hole. Over eons, this slow, steady trickle of radiation causes the black hole to evaporate, gradually shrinking until it potentially vanishes entirely. This was a revolutionary conclusion. Black holes aren't eternal. They have a temperature, they glow, and they eventually die. But this beautiful mechanism created a monstrous problem, the infamous information paradox. In quantum mechanics, information is never truly lost. The quantum state of a system, all the information about the properties of every particle that went into it, must be preserved through any process. This is a principle called unitarity. If you could somehow track every single particle and wave resulting from a complex event, like burning a book, you should in principle be able to reverse the process and reconstruct the original book from the ashes and smoke. The information is scrambled, but it is not destroyed. Now consider a black hole. Imagine you throw a book into it. The book is made of particles, each with specific properties: mass, charge, spin, and quantum state. According to Hawking's calculation, the radiation coming out is purely thermal. It is random noise, its properties determined only by the black hole's mass, charge, and spin. It carries no specific information about whether you threw in a book, a computer, or a collection of feathers. When the black hole finally evaporates and disappears, all that remains is this featureless thermal radiation. The detailed quantum information about everything that ever fell into the black hole seems to have been irretrievably erased from the universe. This violates a core tenet of quantum mechanics, suggesting that our most fundamental theories about how reality works are fundamentally incompatible. The physics community has been grappling with this paradox for decades, and several compelling solutions have been proposed. One leading idea is that the information isn't actually lost, it is somehow encoded on the event horizon itself. The holographic principle suggests that all the information about what fell into the black hole is stored as a two-dimensional pattern on its surface, much like a hologram. As the black hole evaporates, this information is slowly and subtly imprinted onto the outgoing Hawking radiation. It would be imprinted in incredibly complex correlations between the radiation particles, a code so elaborate that to any ordinary measurement, the radiation would still look random and thermal. Only by collecting all the radiation over the black hole's entire multi-billion-year lifespan and analyzing the impossible complexity of how every particle correlates with every other particle could you theoretically decode the story of the book that fell in. This preserves the information in principle, but makes its recovery practically impossible for any conceivable observer. Another fascinating possibility involves no firewalls. If information is to escape, what happens to someone falling into the black hole? The traditional view, based on Einstein's equivalence principle, is that you would cross the event horizon without noticing anything special, no dramatic event, just the inevitable pull toward the singularity. But if information is being encoded on the horizon for release, some theories suggest this process might create a deadly barrier, a firewall of ultra-high energy particles that would instantly incinerate anyone crossing the horizon. This would violate Einstein's principle and create a new paradox, forcing physicists to choose between preserving information and preserving the peaceful experience of an infalling astronaut. The debate rages on, with some researchers proposing that the interior of the black hole doesn't exist at all, or that it is somehow connected to another universe through a wormhole. The resolution of Hawking's paradox is more than an academic exercise. It is a direct assault on the deepest questions about the nature of reality, demanding that we reconcile how the universe handles its own information and whether the past is ever truly gone for good. And so our journey through the unseen architecture of the cosmos draws to a close, having ventured from the seething quantum foam beneath our feet to the dark energy accelerating the universe toward a cold and lonely fate. We've explored 30 fundamental forces, each an invisible sculptor, working in concert across impossible scales to craft the reality we perceive. The quantum vacuum's fleeting particles grant atoms their stability, while the Higgs field's cosmic molasses gives them substance. Dark matter's gravitational scaffold provides the blueprint for galaxies, and dark energy's repulsive push dictates their ultimate destiny. From the spooky, instant connection of entanglement to the patient, universe-spanning ripples of gravitational waves, these are the hidden mechanisms that orchestrate everything from the decay of an atom to the spin of a galaxy. This grand tapestry reveals a universe far stranger and more wondrous than it appears on the surface. It is a cosmos where nothing is truly empty, where observation can freeze change in its tracks, and where the very laws of physics seem precariously or perfectly fine-tuned for our existence. Yet for every mystery we've unraveled, a dozen deeper enigmas remain. We still do not know what dark matter and dark energy actually are, only what they do. The paradox of Hawking radiation challenges our understanding of information itself, and the quest to unite gravity with the quantum realm continues to push the boundaries of human thought. We are like explorers who have just finished mapping the coastline of a vast and unknown continent, aware that the interior holds secrets beyond our current imagination. This is not an end, but an invitation to keep looking, to keep wondering. The greatest discovery is the realization of how much we have yet to learn. Now we want to hear from you. Which of these 30 cosmic forces captured your imagination the most? Was it the holographic principle's suggestion that reality is a projection, or the mind-bending potential of extra dimensions curled up at every point in space? Perhaps it was the existential thrill of vacuum decay, or the quiet, ghostly dance of neutrinos changing their identity as they pass through your body. Share your favorite in the comments below. We read every single one. If this exploration into the hidden layers of reality sparked your curiosity, then you're in the right place. We delve into the biggest mysteries of the universe right here, from the birth of black holes to the fate of the cosmos. Make sure to subscribe and hit the notification bell so you don't miss our next journey into the unknown. The universe is whispering its secrets.